From the farthest galaxies to the smallest particles, from the first moments of existence to the present day, the story of our universe is the greatest tale ever told. It's a narrative that spans nearly 14 billion years, crossing unimaginable distances and delving into the deepest mysteries of existence itself. This is the history of everything that has ever been, and perhaps everything that ever will be. Why should we endeavor to tell this cosmic story? Because we are not merely observers of this grand narrative. We are its children. Every atom in your body, every element that makes up your existence, was forged in the heart of an ancient star. The iron in your blood, the calcium in your bones, the carbon that forms the basis of all life. All of these were created in stellar furnaces that exploded billions of years ago, scattering their enriched remains across the cosmos. When you look up at the night sky, you are looking at your most distant ancestors. Science has become our most reliable narrator for this epic tale. Through centuries of observation, experimentation, and mathematical insight, we have pieced together a remarkable chronicle of cosmic evolution. Telescopes have become our time machines, allowing us to peer billions of light years away, and therefore billions of years into the past. Particle accelerators have recreated conditions not seen since moments after the universe began. Sophisticated computer models have allowed us to visualize processes that unfold over eons in mere moments. Together, these tools have allowed us to reconstruct the history of existence itself with astonishing precision. Yet the sheer scale of cosmic history challenges human comprehension. How can we truly grasp the vastness of 13.8 billion years? If the entire history of the universe were compressed into a single Earth year, with the Big Bang occurring at midnight on January 1st, and the present moment being the final second of December 31st, then all of human civilization would occupy only the last 14 seconds of that cosmic year. The dinosaurs would have gone extinct around December 26th. The first multicellular organisms would have appeared in mid-November, and our Sun and Earth would have formed in early September. The universe has gone through distinct epochs and transformations throughout its history. From an incomprehensibly hot and dense beginning, it has expanded and cooled, allowing for increasingly complex structures to form. The fundamental forces of nature separated. Matter congealed from energy, atoms formed from subatomic particles. Stars and galaxies emerged from primordial gas. Planets coalesced around stars. And on at least one planet, our own Earth, life arose, evolved, and eventually developed the consciousness necessary to contemplate its own origins. We know much about this story, but significant mysteries remain. We still debate what, if anything, existed before the Big Bang. The nature of dark matter and dark energy, which together constitute about 95% of the universe's contents, remains elusive. We don't fully understand how life first emerged from non-living chemistry, and we cannot say with certainty what ultimate fate awaits our universe in the distant future. These gaps in our knowledge aren't failures, they're frontiers. They represent the exciting questions that drive scientific inquiry forward. Our cosmic history can be marked by several key milestones. The Big Bang itself, approximately 13.8 billion years ago, represents the beginning of space, time, matter, and energy as we understand them. About 380,000 years later, the universe cooled enough for atoms to form, allowing light to travel freely for the first time. After hundreds of millions of years of darkness, the first stars ignited, illuminating the cosmos and forging heavier elements. Galaxies formed and evolved, including our own Milky Way. Within our galaxy, our solar system took shape about 4.6 billion years ago. Life emerged on Earth at least 3.5 billion years in the past. And relatively recently, just a few 100,000 years ago, humans evolved the capacity to wonder about all of this. This vast timeline humbles us. It reminds us of our cosmic insignificance in terms of space and time. Yet it also elevates us. In a universe that has existed for nearly 14 billion years, spanning billions of light years in all directions. We have managed to reconstruct this history despite our brief lives and limited senses. We have used our minds to transcend our limitations. Through science, we have become the universe's way of knowing itself. Around 380,000 years after the Big Bang, when the universe had cooled to about 3,000 degrees Kelvin, another pivotal transition occurred. The temperature had finally dropped low enough for electrons to bind with protons, forming stable hydrogen atoms in a process called recombination. As electrons became bound in atoms, photons could suddenly travel freely without being constantly scattered. The universe became transparent to light for the first time. This moment of decoupling between matter and radiation released the oldest light in the universe, the cosmic microwave background radiation that we can still detect today. These ancient photons have been traveling through space ever since, gradually stretched by cosmic expansion until their wavelengths have increased by a factor of about 1,100. What began as visible light has been redshifted into the microwave portion of the electromagnetic spectrum, creating a faint glow that permeates all of space, a direct echo of the Big Bang itself. The cosmic microwave background radiation was first detected accidentally by Arno Penzias and Robert Wilson in 1964, while they were testing a sensitive radio antenna at Bell Laboratories. The persistent background noise they detected, coming equally from all directions in the sky, was soon recognized as the long-predicted thermal radiation left over from the Big Bang. This discovery provided compelling evidence for the Big Bang theory over its main competitor at the time, the steady-state theory, which proposed that the universe had no beginning but was continuously creating new matter as it expanded. Subsequent observations of the cosmic microwave background by satellites like COBE, WMAP, and Planck have revealed subtle temperature variations, differences of just 1 part in 100,000 that correspond to the density fluctuations in the early universe. These tiny variations, expanded from quantum fluctuations during inflation, would serve as the seeds from which all cosmic structure would eventually grow under the influence of gravity. The story of the Big Bang isn't merely a tale of physics and chemistry, it's the origin story for everything we see in today's universe. Every galaxy, every star, every planet, and indeed every atom in our bodies can trace its lineage back to those first crucial moments. The protons in your body have existed, largely unchanged, since the universe was 1 microsecond old. The hydrogen in the water you drink was formed during recombination nearly 14 billion years ago. You are, in the most literal sense, made of Big Bang stuff. This cosmic origin story has been pieced together through decades of careful observation, theoretical insight, and mathematical modeling. The Big Bang theory isn't a mere hypothesis. It's supported by multiple independent lines of evidence: the expansion of the universe, the cosmic microwave background radiation, the abundance of light elements, and the distribution of galaxies across space. These diverse observations converge on a consistent narrative about our cosmic origins, a triumph of human intellect and scientific methodology. Yet mysteries remain. While we understand much about how the universe evolved from its first few seconds onward, the exact nature of the beginning itself, the first 10 to the negative 43 seconds, known as the Planck epoch, remains beyond our current theoretical understanding. At this scale, both quantum mechanics and general relativity would have been important, but these two fundamental theories of physics have not yet been successfully unified into a quantum theory of gravity. Until such a theory emerges, the first instant of creation remains at the frontier of scientific knowledge. Similarly, while inflation elegantly explains many observed features of our universe, the exact mechanism behind it remains an active area of research. What was the inflaton field? Why did it exist in an unstable state? Did inflation happen just once, or does it continue eternally in regions beyond our observable universe, spawning new cosmic domains with potentially different physical laws? These questions connect the Big Bang to the multiverse theories we explored when considering what might have existed before our universe began. The Big Bang also raises profound philosophical questions. Was the beginning of our universe also the beginning of time itself? If so, questions about before the beginning may be fundamentally incoherent. Is our universe unique or one of many? Does the remarkable fine-tuning of physical constants that allows for complex structures like stars, planets, and ultimately life reflect chance, necessity, or design? These questions lie at the intersection of cosmology, philosophy, and even theology, reminding us that the Big Bang narrative touches on our deepest wonderings about existence itself. What's clear is that our universe had a beginning, a moment when everything we observe today, from subatomic particles to superclusters of galaxies, was compressed into a state of extraordinary density and temperature. From this singular origin, through processes we understand with remarkable precision, the cosmos expanded, cooled, and evolved into the vast, complex structure we inhabit today. The story of the Big Bang reminds us that the universe is not static, but dynamic. It has a history and a direction. It began hot and dense, and has been expanding and cooling ever since. This cosmic evolution continues today, with galaxies still moving apart from one another, the average temperature of space still gradually falling, and structure still forming under the influence of gravity. We live not in a completed cosmos, but in an ongoing process of creation and evolution. As the universe expanded and cooled after recombination, it entered a phase known as the Cosmic Dark Ages, a period when the first atoms had formed, but stars had not yet ignited to illuminate the cosmos. During this era, from about 380,000 years to about 100 million years after the Big Bang, the universe was filled primarily with neutral hydrogen and helium gas, gradually clumping together under the influence of gravity, but emitting no visible light. This period marked a transition from the relatively smooth, uniform early universe to the richly structured cosmos we observe today. The tiny density fluctuations preserved in the cosmic microwave background, those quantum jitters stretched by inflation to macroscopic scales, began their slow gravitational collapse. Slightly denser regions attracted more matter, becoming denser still, while less dense regions became increasingly empty. Thus began the formation of the cosmic web, the large-scale structure of filaments, clusters, and voids that characterizes the distribution of matter in today's universe. The Big Bang represents not just our cosmic origin, but perhaps the greatest scientific detective story ever told. Starting with the observation that distant galaxies are moving away from us, scientists have reconstructed events that occurred billions of years before human existence, tracking the evidence backward through time to conditions so extreme they challenge our imagination. This intellectual journey stands as one of humanity's greatest achievements, connecting us to our deepest cosmic roots and situating our brief existence within the grand narrative of universal evolution. As we continue our journey through cosmic history, we leave behind the extreme conditions of the Big Bang and venture into the era when the first stars and galaxies began to form. But we carry with us the knowledge that everything we will encounter, every structure, every process, every element heavier than lithium, emerged from the conditions established in those first crucial moments. The Big Bang was not just an event in the distant past. It is the foundation upon which the entire subsequent history of the universe has unfolded. In the vastness of cosmic history, a pivotal moment occurred approximately 380,000 years after the Big Bang, a moment when light, previously trapped in a dense plasma of charged particles, suddenly broke free to travel across the expanding universe. This ancient light, stretched by nearly 14 billion years of cosmic expansion, still bathes our world today as the cosmic microwave background radiation. It is the oldest light in the universe, a direct glimpse of conditions when the cosmos was in its infancy, and it tells a remarkable story about our origins. To understand this first light, we must first grasp why the early universe was opaque. In the first few 100,000 years after the Big Bang, the universe was far hotter than the center of any star we know today. At temperatures above 3,000 degrees Kelvin, matter existed primarily as a plasma, a soup of free electrons and nuclei. unable to form stable atoms. In this environment, photons, particles of light, couldn't travel far before colliding with an electron, being scattered in a random direction, only to collide again moments later with another electron. Light was effectively trapped, constantly bouncing between charged particles in a cosmic pinball machine. The universe during this era resembled the interior of the sun, blindingly bright yet completely opaque. If you could somehow have survived the extreme conditions and opened your eyes, you would have seen only a brilliant, featureless glow in all directions. No stars, no galaxies, no structure of any kind would have been visible, just an all-encompassing luminous fog. The cosmos was a place of extraordinary uniformity, with only the slightest variations in density and temperature, variations that would later prove crucial for the formation of all structure. As the universe continued its relentless expansion, this plasma gradually cooled. By 380,000 years after the Big Bang, the temperature had fallen to about 3,000 degrees Kelvin, comparable to the surface of a relatively cool star. At this crucial threshold, something profound happened. Electrons could finally bind with protons to form stable hydrogen atoms in a process astronomers call recombination. The term recombination is something of a misnomer, since electrons and protons had never before combined in the history of the universe. Nevertheless, this name has stuck for this critical phase transition when the charged plasma neutralized into the first true atoms. As electrons became bound within these newly formed atoms, they were no longer free to interact with passing photons. Suddenly, the universe became transparent. This moment of decoupling, when matter and radiation parted ways, released what we now call the cosmic microwave background radiation. Light that had been trapped in the cosmic fog was suddenly set free to travel through space, largely unimpeded. Those primordial photons had been journeying through the expanding cosmos ever since, growing progressively redder and cooler as space itself stretches, shifting their wavelengths toward the longer, lower energy end of the electromagnetic spectrum. What began as visible light, glowing with the yellowish-white hue of a 3,000 degree Kelvin surface, similar to a light bulb, has been stretched by a factor of more than 1,100 by cosmic expansion. Today, these ancient photons have cooled to just 2.725 Kelvin, approximately minus 270 degrees Celsius, and their wavelengths have shifted from the visible spectrum into the microwave region. The first light has become a faint microwave glow permeating all of space. This cosmic microwave background radiation is remarkably uniform, with the same temperature in all directions to within 1 part in 100,000. Such extraordinary uniformity provides strong evidence for the hot Big Bang model and the inflationary period that preceded it. Without inflation to smooth out the primordial universe, we would expect to see much larger temperature variations in different regions of the sky. The uniformity of the cosmic microwave background confirms that the entire observable universe was once in causal contact, part of a much smaller region before inflation stretched it beyond the horizon. Yet the cosmic microwave background is not perfectly uniform, and these subtle variations hold the keys to understanding cosmic structure. Exquisitely sensitive instruments have mapped tiny temperature fluctuations, places where the background radiation is slightly hotter or cooler than average. These fluctuations reflect density variations in the early universe, regions where matter was slightly more or less concentrated when the first atoms formed. These temperature differences are incredibly small, typically just a few dozen microkelvin, millionths of a degree, above or below the average. If our eyes could see microwave radiation, the cosmic microwave background would appear as a nearly uniform glow across the entire sky, with only the subtlest mottling of slightly warmer and cooler patches. Yet these minute variations, amplified by gravity over billions of years, would eventually grow into all the structure we see today, from the largest superclusters of galaxies to the smallest dwarf stars. The discovery of the cosmic microwave background radiation ranks among the most significant scientific finds of the 20th century. In 1964, Radio astronomers Arno Penzias and Robert Wilson were testing a sensitive microwave receiver at Bell Laboratories in New Jersey. They encountered a persistent background noise, a faint signal coming equally from all directions in the sky, which they initially mistook for interference. After ruling out various sources of error, including pigeons nesting in their antenna, they realized they had stumbled upon something profound. At nearby Princeton University, physicist Robert Dicke and his colleagues had been designing an experiment specifically to search for this radiation, which had been predicted years earlier as a consequence of the Big Bang theory. When Dicke learned of Penzias and Wilson's discovery, he reportedly told his team, "Well, boys, we've been scooped." The two groups published companion papers, with Penzias and Wilson describing their observation and Dicke's team explaining its cosmological significance. For this accidental discovery of the cosmic microwave background, Penzias and Wilson would later receive the Nobel Prize in Physics. This detection provided compelling evidence for the Big Bang theory over its main competitor at the time, the steady-state theory. While the steady-state theory proposed a universe without beginning or end, continuously creating new matter as it expanded, it offered no explanation for this all-pervasive microwave radiation. The Big Bang theory, however, had specifically predicted such radiation as the cooled remnant of the universe's hot, dense, early phase. The discovery of the cosmic microwave background radiation thus helped cement the Big Bang as the standard model of cosmology. Subsequent observations have refined our understanding of this primordial light. In 1989, NASA launched the Cosmic Background Explorer COBE satellite, which confirmed that the spectrum of the radiation matched exactly what would be expected from a nearly perfect blackbody, an object that absorbs and emits radiation with maximum efficiency. This perfect blackbody spectrum, with its temperature of 2.725 Kelvin, provided further evidence that the radiation originated from a hot, dense state in the early universe, rather than from any other astrophysical process. COBE also detected the first evidence of those crucial temperature fluctuations, the seeds of cosmic structure. Later missions, including the Wilkinson Microwave Anisotropy Probe, WMAP, and the European Space Agency's Planck satellite, mapped these fluctuations with increasing precision. The resulting maps of the cosmic microwave background show a pattern of hot and cold spots that reflect the distribution of matter when the universe was just 380,000 years old, a baby picture of our cosmos. The statistical properties of these fluctuations reveal a wealth of information about the universe's composition, geometry, and evolution. By analyzing the size and distribution of the hot and cold spots, cosmologists can determine the total amount of matter and energy in the universe, the rate of cosmic expansion, and even the universe's ultimate fate. The cosmic microwave background thus serves as a powerful tool for precision cosmology, allowing us to measure fundamental parameters of our universe with remarkable accuracy. These measurements have led to the current standard model of cosmology, which suggests that ordinary matter, the stuff of stars, planets, and people, makes up only about 5% of the universe's total energy content. The remaining 95% consists of dark matter, about 27%, and dark energy, about 68%, components whose nature remains one of the great unsolved mysteries in physics. The cosmic microwave background provides some of our strongest evidence for the existence of these enigmatic substances. Beyond its role in confirming the Big Bang and constraining cosmological parameters, the cosmic microwave background radiation holds deeper significance. It represents a moment of transition, a boundary between the earlier universe, which was a hot, opaque plasma where no complex structures could exist, and the later universe, where matter could clump together under gravity to form stars, galaxies, and eventually us. The cosmic microwave background marks the moment when the universe first became visible to itself. The light from the cosmic microwave background also serves as a kind of ultimate horizon for our observations. We cannot directly observe anything from earlier than this decoupling era, because the universe was opaque to electromagnetic radiation before this time. While other messengers, such as neutrinos or gravitational waves, might someday allow us to probe earlier epochs, the cosmic microwave background represents the limit of what we can see with conventional telescopes. It is, in a sense, the edge of the observable electromagnetic universe. As this ancient light journeyed across the expanding cosmos, it encountered various structures that left their imprints on its pattern. By studying subtle effects like gravitational lensing, the bending of light by massive objects in the cosmic microwave background, scientists can map the distribution of matter between us and this distant surface. The cosmic microwave background thus serves not only as a snapshot of the early universe, but also as a backlight illuminating cosmic structure along its 14 billion-year journey to our telescopes. One fascinating aspect of the cosmic microwave background is that it provides evidence for quantum processes operating on cosmic scales. The pattern of temperature fluctuations we observe appears to have originated from quantum fluctuations, minute uncertainties in energy levels arising from the Heisenberg uncertainty principle that were dramatically amplified by inflation to macroscopic scales. When we look at the cosmic microwave background, we are seeing quantum mechanics written across the sky. Subatomic phenomena blown up to the size of galaxy clusters, the formation of the first atoms that accompanied the creation of the cosmic microwave background represents another crucial milestone, the beginning of chemistry. Before recombination, the universe contained only bare nuclei and free electrons, no true atoms, much less molecules. After recombination, with stable hydrogen and helium atoms now abundant, the stage was set for the first simple molecules to form. Billions of years later, the complex chemistry that would enable life could begin to develop. The cosmic microwave background radiation also helps us understand our place in the universe's history. The fact that we can still detect this radiation today means we live relatively early in cosmic history. In the distant future, as cosmic expansion continues to accelerate, this background radiation will be stretched to ever longer wavelengths, eventually becoming undetectable to even our most sensitive instruments. Future civilizations, should they exist, might have no direct observational evidence of the Big Bang. We are fortunate to live in an era when the universe's origin story remains written across our sky, waiting to be read by anyone with the right instruments. The light from the cosmic microwave background has touched every part of the observable universe. The photons now reaching our detectors from one direction pass through what would become our Milky Way galaxy, while photons from the opposite direction pass through what would become the most distant galaxies we can observe. These ancient light particles have completed a journey spanning nearly the entire history and breadth of our cosmos before ending their travels in our telescopes. They are the most well-traveled messengers in the universe. Although the cosmic microwave background marks the moment when light could first travel freely, the universe remained dark in a functional sense. No stars yet shone, no galaxies yet glowed with the light of billions of suns. The universe was filled primarily with neutral hydrogen and helium gas, slowly clumping together under the influence of gravity, guided by those subtle density variations imprinted in the cosmic microwave background. This era, following recombination, is known as the Cosmic Dark Ages, a period when the first atoms had formed, but stars had not yet ignited to illuminate the cosmos. This dark period would last for millions of years, as gravity gradually drew matter together into denser and denser concentrations. The slightly denser regions seen in the cosmic microwave background, those tiny temperature fluctuations, served as the seeds for all cosmic structure. Within these regions, gas began to collapse under its own gravity, forming the first massive concentrations of matter. Eventually, the conditions at the centers of these collapsing gas clouds would become extreme enough to ignite nuclear fusion, and the first stars would burst into existence, ending the cosmic dark ages. The cosmic microwave background thus stands as a boundary monument between eras, marking the transition from the early, smooth, plasma-dominated universe to the later, structured, atom-dominated universe. It represents the moment when the cosmos shifted from being radiation-dominated to matter-dominated. allowing gravity to begin its work of creating complexity from simplicity, structure from near uniformity. When we observe the cosmic microwave background today, we are looking at a spherical shell surrounding us in all directions, representing a specific moment in cosmic history, the moment of decoupling, when the universe first became transparent. This shell, known as the surface of last scattering, is located at a distance of approximately 13.8 billion light-years from Earth in all directions. It represents the most distant thing we can directly observe using electromagnetic radiation. Remarkably, the cosmic microwave background radiation reaches us from all directions with nearly the same intensity. This observation confirms another key prediction of the Big Bang theory, that the universe has no center and no edge. If the Big Bang had been an explosion in pre-existing space, we would expect to see the cosmic microwave background concentrated in one direction, the direction of the explosion. Instead, we see it uniformly in all directions, confirming that the Big Bang happened everywhere at once, with space itself expanding from every point. The subtle patterns in the cosmic microwave background also reveal the universe's overall geometry. Just as we can determine whether a surface is flat or curved by studying the properties of triangles drawn on that surface, cosmologists can determine whether space itself is flat or curved by analyzing the size distribution of hot and cold spots in the cosmic microwave background. These observations strongly suggest that the universe is flat, or very nearly so, another key prediction of inflationary models. As our instruments have become more sensitive, scientists have detected additional subtle features in the cosmic microwave background beyond simple temperature fluctuations. One such feature is polarization, a preferred orientation in the radiation's electromagnetic waves. Different processes can induce different patterns of polarization, and by studying these patterns, researchers hope to find evidence of gravitational waves from the inflationary epoch itself. Ripples in space-time from the universe's first instance that would have left a distinctive imprint on the cosmic microwave background. The detailed study of the cosmic microwave background continues to be an active area of research, with new experiments being designed to measure ever more subtle features. These investigations may ultimately help resolve some of the deepest questions in physics, including the nature of dark matter and dark energy, the validity of inflation theory, and potentially even the quantum nature of gravity itself. The oldest light in the universe may yet reveal some of nature's deepest secrets. As the universe transitioned from its early opaque state to the transparent cosmos we observe today, the stage was set for the formation of the first stars and galaxies. The cosmic microwave background provides our last direct glimpse of the universe before these structures began to form. After recombination, the universe entered the cosmic dark ages, a period lasting hundreds of millions of years, during which matter slowly condensed under the influence of gravity, guided by those tiny density fluctuations we now observe in the cosmic microwave background. During these dark ages, the universe was filled primarily with neutral hydrogen and helium, with no sources of visible light. As matter continued to clump together in the denser regions, the first proto-galaxies began to take shape, vast clouds of gas slowly contracting under gravity's pull. Within these clouds, even denser regions would eventually collapse to form the first stars, finally ending the cosmic dark ages and bringing light back to the universe approximately 150 million years after the Big Bang. The cosmic microwave background thus represents both an ending and a beginning. The end of the universe's earliest phase, when it was too hot and dense for atoms to form, and the beginning of the long process of structure formation that would eventually lead to galaxies, stars, planets, and life. It marks the moment when the universe first became transparent, setting the stage for all the cosmic evolution that would follow. As we continue our journey through cosmic history, we move from the moment of first light into the dark ages that followed, a time when the universe, though transparent, still awaited the first stars to illuminate the cosmic night. The transition from the bright, opaque, early universe to the darkness that followed recombination set the stage for the next great chapter in cosmic evolution. the formation of the first luminous objects that would transform the simple universe of hydrogen and helium into the rich, complex cosmos we inhabit today. After the release of the cosmic microwave background radiation, approximately 380,000 years after the Big Bang, the universe entered a profound and mysterious era known as the Cosmic Dark Ages. For the first time, space was transparent. Photons could travel freely without constantly scattering off free electrons. Yet paradoxically, the cosmos had gone dark. No stars shone. No galaxies glimmered in the cosmic night. The universe had become a vast, expanding sea of neutral hydrogen and helium gas, slowly cooling and gradually clumping together under the influence of gravity. This era represents one of the most significant gaps in our observational record of cosmic history. While we can directly observe the cosmic microwave background from the moment of recombination, and we can see fully formed galaxies from when the universe was less than 1 billion years old, the intervening dark ages remain largely hidden from our view. This period, spanning hundreds of millions of years, saw the crucial transition from the smooth, nearly uniform early universe to the richly structured cosmos we inhabit today. Why did the universe go dark? The answer lies in the physics of light and the state of matter during this era. At recombination, when the universe cooled sufficiently for electrons to bind with protons forming neutral hydrogen atoms, the primordial plasma that had previously filled space was transformed into neutral gas. This neutralization made the universe transparent. Photons could suddenly travel vast distances without being scattered, but the same process eliminated the main source of light. The hot, glowing plasma that had previously illuminated the cosmos with its incandescent brilliance was gone, replaced by cool, dark gas. The radiation released at this moment, what we now observe as the cosmic microwave background, quickly shifted to longer wavelengths as the universe continued to expand. What began as visible light soon stretched into the infrared and then into the microwave part of the spectrum. The universe, though filled with this radiation, would have appeared completely dark to human eyes. A vast, empty void of neutral atoms with no visible light sources. During this era, the matter in the universe was distributed almost uniformly, but not quite. Those tiny temperature fluctuations we observe in the cosmic microwave background, variations of just 1 part in 100,000, reflected slightly higher and lower densities in the primordial matter distribution. These subtle differences, initially quantum fluctuations magnified by inflation, would serve as the seeds for all future structure. In the denser regions, gravity would gradually pull additional matter inward, making them denser still. The less dense regions would surrender their matter to these growing concentrations, becoming even more rarefied. This process of gravitational instability, dense regions becoming denser while sparse regions become sparser, proceeded slowly at first. In the early universe, radiation pressure could effectively resist gravity's pull, preventing matter from clumping together too quickly. But as the universe expanded and cooled, matter began to dominate over radiation, and gravity's influence became increasingly important. The subtle ripples in the density of the universe began to grow more pronounced. Here, a mysterious component of the universe played a crucial role: dark matter. Unlike ordinary matter, which physicists call baryonic matter, dark matter doesn't interact with light or other forms of electromagnetic radiation. We can't see it directly, but we can infer its presence through its gravitational effects. Observations of galaxy rotation rates, gravitational lensing, and the cosmic microwave background itself all point to the existence of this invisible substance, which appears to outweigh ordinary matter by a factor of roughly 5 to 1. Because dark matter doesn't interact with radiation, it began clumping together under gravity's influence much earlier than ordinary matter. While the pressure of photons could temporarily halt the collapse of hydrogen and helium gas, dark matter felt no such resistance. It began forming a cosmic scaffold, a network of filaments and nodes where density was higher than average. This dark matter web would ultimately guide the distribution of ordinary matter, creating a framework upon which the visible universe would later be built. Computer simulations reveal how this process might have unfolded, starting with the tiny density fluctuations observed in the cosmic microwave background. Scientists can model how gravity would have shaped the evolution of both dark and ordinary matter over hundreds of millions of years. These simulations show the emergence of a cosmic web structure, vast filaments of dark matter intersecting at dense nodes with relative voids between them. This pattern, first forming in dark matter and later followed by ordinary gas, matches remarkably well with the large-scale structure we observe in today's universe. As ordinary matter fell into the gravitational wells created by dark matter, gas began to pool in the densest regions. The most massive accumulations of dark matter, what we now call dark matter halos, attracted the most gas. Within these halos, the gas was compressed, heated by gravitational energy, converted to thermal energy, and began the long process of cooling and further condensation that would eventually lead to the first stars. The cooling of this gas represents another critical process during the Dark Ages. For gas to collapse all the way to stellar densities, it must shed excess heat. In today's universe, gas can cool efficiently through interactions with heavy elements like carbon, oxygen, and iron, which radiate energy away as they collide with other particles. But in the primordial universe, no such elements existed. The only available cooling mechanisms involved hydrogen and helium. Hydrogen molecules, two hydrogen atoms bonded together, proved especially important for this early cooling. Though rare in the primordial universe, these molecules could form in trace amounts through reactions catalyzed by free electrons left over from recombination. Hydrogen molecules can rotate and vibrate, absorbing and emitting energy at specific wavelengths. This property allowed primordial gas clouds to radiate away excess heat, enabling further collapse toward the densities needed for star formation. As gas cooled and condensed in the densest regions of dark matter halos, it began to fragment into multiple clumps. The physics of this fragmentation process would determine the masses of the first stars, a crucial parameter that would influence their brightness, their lifetimes, and the elements they would eventually produce through nuclear fusion. Current models suggest that these first stars, forming from pristine hydrogen and helium with minimal cooling efficiency, would have been dramatically different from the stars we see today. Unlike modern stars, which range from red dwarfs less than a tenth the mass of our Sun to blue supergiants, more than 100 times as massive, the first stars likely formed primarily at the high-mass end of the spectrum. With typical masses perhaps 30 to 300 times that of our Sun, these behemoths would have been extraordinarily hot, bright, and short-lived compared to stars today. Astronomers call them population 3 stars, the first generation of stars, composed entirely of primordial hydrogen and helium. Throughout the Dark Ages, the vast majority of the universe remained filled with neutral hydrogen. This gas was not completely invisible. It absorbed and emitted radiation at a specific wavelength corresponding to a quantum transition in the hydrogen atom. This radiation, with a wavelength of 21 centimeters, provides one of the few potential windows into the Dark Ages. As cosmic expansion has stretched these radio waves to much longer wavelengths today, astronomers hope that next-generation radio telescopes might detect this signal, mapping the distribution of hydrogen during this otherwise invisible era. The duration of the cosmic dark ages remains somewhat uncertain. Most models suggest that the first stars began to form roughly 100 to 200 million years after the Big Bang, gradually ending the darkness. However, the transition was not instantaneous. The first stars, though incredibly bright individually, were rare and widely scattered. Their light and energy gradually began to transform the universe, but this process would take additional hundreds of millions of years to complete. This transformation began as ultraviolet radiation from the first stars started to rayonize the neutral hydrogen around them. The intense light from these massive hot stars stripped electrons from nearby hydrogen atoms, creating bubbles of ionized plasma around each star. Initially small, these ionized regions gradually expanded, and eventually merged as more stars formed and the process accelerated. This era of reionization marks the end of the cosmic dark ages and the beginning of the universe as we might recognize it today. A cosmos filled with luminous objects. The cosmic dark ages represent more than just a gap in our observational record. They embody a profound transition in the character of the universe itself. During this era, the cosmos evolved from the smooth, radiation-dominated early universe, governed by plasma physics, to the structured, matter-dominated universe, shaped by gravity and nuclear processes. It was a time when complexity began to emerge from simplicity, when the seeds planted in the first moments after the Big Bang began to grow into the rich cosmic ecosystem we inhabit today. Despite the darkness, this era was far from static. The continuous expansion of the universe, the gradual growth of density fluctuations, the accumulation of gas in dark matter halos, the cooling and fragmentation of this gas, all these processes were actively reshaping the cosmos, preparing it for the dramatic transformations to come. The Dark Ages were less a pause in cosmic evolution than an essential preparatory phase, setting the stage for the next act in the cosmic drama. One of the most remarkable aspects of this era was its simplicity compared to later epochs. The chemistry of the universe was elemental in the most literal sense. Hydrogen and helium dominated, with only trace amounts of lithium and beryllium produced during Big Bang nucleosynthesis. No heavier elements existed yet. Those would wait for the nuclear furnaces of stars to forge them. The physics was similarly straightforward, gravity pulling matter together while gas pressure and the expansion of space resisted this collapse. This relative simplicity makes the Dark Ages more amenable to theoretical modeling than later eras, despite the observational challenges. As astronomers and cosmologists seek to understand this mysterious period, they employ multiple approaches. Theoretical models based on well-established physics allow us to predict how matter should have evolved under gravity's influence. Computer simulations let us watch this evolution unfold in virtual universes that mimic our own. And new observational techniques promise to provide direct evidence, particularly through the 21-centimeter radiation from neutral hydrogen, which carries information about the state and distribution of gas during these dark ages. Several ambitious projects aim to detect this faint radio signal, including the Square Kilometre Array and the Hydrogen Epoch of Reionization Array. These instruments face formidable challenges. The signal is extremely weak and masked by much stronger radio emissions from our own galaxy and from human technology. Yet the potential scientific payoff is enormous. Detecting this radiation would provide the first direct observations of the universe during this mysterious era, potentially revolutionizing our understanding of cosmic evolution. The Dark Ages also offer a unique opportunity to test theories of dark matter and dark energy. Different models for these mysterious components predict subtle differences in how structure would have formed during this era. By observing the distribution and properties of the first luminous objects that emerged from the Dark Ages, we might constrain these models, perhaps solving some of the greatest remaining mysteries in cosmology. As gas continued to accumulate in dark matter halos, the densest regions reached a critical threshold. When the central temperature and density became high enough, nuclear fusion ignited, hydrogen nuclei fused to form helium, releasing enormous energy in the process. The first stars were born, their brilliant light piercing the cosmic darkness for the first time since recombination, some 150 million years after the Big Bang. These first stars were cosmic pioneers, illuminating a universe that had never known starlight before. They were also cosmic alchemists, the first objects to forge elements heavier than those produced in the Big Bang. In their cores, through the nuclear fusion that powered their brilliant light, they transformed primordial hydrogen and helium into carbon, oxygen, silicon, iron, and other elements essential for planets and life. When these massive stars died in spectacular supernova explosions after only a few million years, they seeded their surroundings with these newly created elements, enriching the cosmos and forever changing its chemistry. The emergence of these first stars marks the end of the cosmic dark ages and the beginning of the epoch of reionization, a period when starlight gradually transformed the neutral universe back into an ionized state, but with a crucial difference. Unlike the uniform ionized plasma before recombination, this new ionized medium was structured with dense regions and voids, clusters and filaments. Complexity had emerged from the darkness, and the universe would never be simple again. Our cosmic origin story also unites us. The borders drawn on Earth's maps, the cultural differences that sometimes divide us, even the biological distinctions between species, all seem trivial when viewed against the backdrop of cosmic history. Every living thing on Earth shares a common ancestry. Every human being is made of stardust. We are all, in the most literal sense, children of the cosmos. As we embark on this journey through time, we will travel from the very first moments of creation to the present day, and even peer into possible futures. We will witness the birth of stars and the death of worlds. We will see how the simplest particles combine to create the wondrous complexity we observe today. We will trace the lineage of our sun, our planet, and ourselves back to their cosmic origins. The history of the universe is written in light and gravity, in the atomic composition of meteorites, in the radiation that permeates all of space, and in the very laws of physics themselves. By learning to read these cosmic signatures, we have uncovered our place in the grand scheme of existence. This knowledge doesn't diminish the wonder of creation, it enhances it. Understanding the mechanisms behind a rainbow doesn't make it any less beautiful. Knowing how stars shine doesn't make them any less magnificent. As we tell this story, we will encounter scales of time and space that defy easy comprehension. We will discuss temperatures ranging from the unimaginably hot, trillions of degrees in the first moments after the Big Bang, to the desperately cold depths of intergalactic space, just a fraction of a degree above absolute zero. We will travel from subatomic realms measured in femtometers, that's a millionth of a billionth of a meter, to cosmic structures spanning billions of light years. Through it all, we will seek to convey not just the facts of cosmic history, but the awe and wonder it inspires. The story of the universe is not separate from our own stories. It is the backdrop against which all human drama unfolds. Every civilization has created myths and legends to explain the cosmos. Our scientific understanding represents the latest and most accurate version of humanity's quest to comprehend our origins. But like all good origin stories, it inspires deep questions. Why is there something rather than nothing? Why does the universe follow these particular laws and not others? Are we alone in this vast cosmos? What purpose, if any, does all of this serve? Science cannot fully answer these philosophical questions, but it provides the essential context for asking them meaningfully. By understanding what the universe is and how it has evolved, we can better contemplate our place within it. The cosmic perspective doesn't solve all mysteries, but it puts our human concerns into proper proportion. As we journey backward toward the beginning of time itself, we will encounter phenomena that challenge our intuitions. Quantum fluctuations, space-time warping, particles popping in and out of existence. The early universe operated according to rules that seem alien compared to our everyday experience. Yet these exotic processes were essential for creating the conditions that would eventually allow for our existence. The strange becomes familiar when we recognize that without these cosmic oddities, we would not be here to ponder them. Contemplating cosmic history also invites us to consider cosmic futures. The universe of tomorrow will differ from the universe of today. Stars will burn out, galaxies will collide and merge, the expansion of space may continue to accelerate. On shorter timescales, our own sun will eventually exhaust its nuclear fuel, expanding to become a red giant before shrinking to a white dwarf. Earth's habitability will not last forever. The long-term survival of life and of consciousness may depend on our ability to extend our presence beyond our home planet. This perspective can inspire both humility and determination. We are temporary arrangements of atoms, living on a small planet orbiting an average star in one galaxy among billions. Yet we have deciphered the cosmic code to a remarkable degree. We have traced our origins back to the first moments of creation, and we may yet shape the future of life in our corner of the cosmos, serving as conscious stewards of the universe's ongoing evolution. As we stand at this unique moment in cosmic history, able to look back with scientific clarity and forward with technological capability, we face a profound responsibility. We are the first species on Earth with the power to either ensure or extinguish the continuation of complex life. Our decisions in the coming centuries may determine whether consciousness persists or perishes in our corner of the universe. This cosmic context gives our present actions a significance that transcends our brief individual lives. As we look out across the cosmos today, peering back toward the beginning of time, we see light from stars and galaxies that formed after the cosmic dark ages. The darkness itself remains largely invisible to our telescopes, a frontier of modern cosmology. Yet this era, when the universe hovered between pristine simplicity and emergent complexity, holds the answers to fundamental questions about our cosmic origins. The cosmic dark ages remind us that much of the universe's history unfolded in darkness, invisible to any observers that might have existed. The seemingly empty void between the first light, the cosmic microwave background, and the first stars was actually a crucible of creation, where gravity's patient hand slowly molded the featureless early universe into the structured cosmos we inhabit. In the apparent emptiness, the foundations of all future cosmic structures were being laid, atom by atom, in a dance orchestrated by invisible dark matter. As we continue our journey through cosmic history, we emerge from these dark ages into a universe increasingly illuminated by stars and galaxies. The light we now see across the cosmos, from the brilliant blue of massive young stars to the warm glow of spiral galaxies, represents the universe's transition from darkness to luminosity, from simplicity to complexity, from potentiality to actuality. This light tells the story of how a nearly featureless gas of hydrogen and helium, guided by the invisible hand of dark matter, transformed into the rich cosmic ecosystem that ultimately enabled our existence. The cosmic dark ages, lasting from approximately 380,000 years to 150 million years after the Big Bang, represent a critical transition in the evolution of our universe. During this era, the first atoms condensed from plasma, gravity began to amplify tiny density fluctuations, gas collected in dark matter halos, and the stage was set for the formation of the first stars. Though hidden from direct observation, this period bridges the gap between the primordial universe we see in the cosmic microwave background and the structured cosmos we observe in distant galaxies. As the first stars began to shine, they ended the cosmic dark ages and initiated the next major phase of cosmic evolution. Their intense ultraviolet radiation began to strip electrons from the surrounding neutral hydrogen, creating expanding bubbles of ionized gas. This process, called rionization, would eventually transform the entire universe, making it transparent to ultraviolet light and establishing conditions somewhat similar to those we observe today. These first luminous objects, massive, brilliant stars unlike anything in our current galaxy, were the harbingers of a dramatic transformation. They were the universe's first sources of elements heavier than lithium, the first objects to emit significant ultraviolet radiation, and the seeds around which the first galaxies would form. As we leave the cosmic dark ages behind, we enter an era of increasing light and complexity, a time when the universe truly began to resemble the cosmos we recognize today. After hundreds of millions of years of darkness, the universe was about to experience a dramatic transformation. Approximately 150 to 200 million years after the Big Bang, the first stars ignited, their brilliant ultraviolet light piercing the cosmic night. These luminous pioneers marked the end of the cosmic dark ages and the beginning of a new era, one that would ultimately lead to the rich, complex universe we inhabit today. The birth of the first stars was a watershed moment in cosmic history. Before these stellar beacons ignited, the universe consisted almost entirely of hydrogen and helium, with trace amounts of lithium, elements forged in the first few minutes after the Big Bang. No heavier elements existed. No sources of visible light illuminated the vast cosmic expanses. The universe was a dark, relatively simple place, slowly becoming more structured as gravity pulled matter into increasingly dense concentrations. The formation of these first stars, known to astronomers as population 3 stars, occurred in the densest regions of the early universe, places where dark matter had pulled in significant amounts of primordial gas. Within these dark matter halos, hydrogen and helium gradually condensed, becoming denser and hotter. When the temperature and density at the center of these gas clouds reached critical thresholds, approximately 10 million degrees Kelvin, nuclear fusion ignited and stars were born. These first stars were unlike any that exist in our galaxy today. Modern computer simulations suggest they were giants, with masses typically ranging from 30 to 300 times that of our Sun. This extraordinary mass was a direct consequence of the primordial conditions in which they formed. The lack of heavy elements meant that gas could not cool efficiently, resulting in warmer, larger gas clouds that formed correspondingly massive stars. Without metals like carbon and oxygen to radiate away heat, fragmentation into smaller clumps was suppressed, favoring the formation of these stellar behemoths. Their enormous mass made these first stars extraordinarily hot and brilliant. They would have burned with a fierce blue-white light, emitting primarily in the ultraviolet portion of the electromagnetic spectrum. A typical population 3 star might have shone with the brightness of 1,000,000 suns, despite being composed of only the simplest elements. Their surface temperatures likely exceeded 50,000 degrees Kelvin, more than 8 times hotter than our own relatively cool sun. Yet these brilliant cosmic pioneers lived fast and died young. While a star like our Sun can shine steadily for about 10 billion years, the first stars exhausted their nuclear fuel in just a few million years, a mere cosmic eye blink. Their tremendous mass accelerated all aspects of stellar evolution. They burned hotter, brighter, and much more quickly than smaller stars, racing through their life cycles at a dramatically accelerated pace. During their brief lives, these stars accomplished something remarkable. They became the universe's first factories for elements heavier than lithium. Through nuclear fusion in their cores, they transformed primordial hydrogen and helium into carbon, oxygen, silicon, and eventually iron. For the first time in cosmic history, the elements essential for planets and life were being forged in these stellar furnaces. The universe had taken its first step toward chemical complexity. When these massive first stars reached the end of their short lives, they died spectacularly. Too massive to end as white dwarfs or neutron stars, most exploded as supernova or directly collapsed into black holes. Some may have ended as particularly energetic explosions called hypernovae, or even pair instability supernovae, extraordinarily powerful events that would have been visible across much of the observable universe. These explosive deaths scattered the newly forged elements into the surrounding gas, enriching the cosmos with the first metals. Astronomers use the term metals to refer to all elements heavier than helium. This process of stellar enrichment would continue through successive generations of stars, each contributing to the growing chemical complexity of the universe. Every heavy atom in our bodies today, the carbon in our cells, the oxygen we breathe, the iron in our blood, was created inside a star and released in its death throes. The first stars began this essential process of cosmic enrichment. The intense ultraviolet radiation from these massive stars had another profound effect. It began to rayonize the neutral hydrogen that filled the universe. The high-energy photons from population 3 stars stripped electrons from nearby hydrogen atoms, creating expanding bubbles of ionized plasma around each star. This process, called rayonization, gradually transformed the universe from a dark sea of neutral gas back into an ionized state. though now with complex structure rather than the uniform plasma that existed before recombination. Initially, these ionized regions were isolated islands in a largely neutral universe. But as more stars formed, and eventually the first galaxies assembled, these bubbles grew larger and began to overlap. Approximately 500 million to 1 billion years after the Big Bang, reionization was complete, and the universe became largely transparent to ultraviolet light, a state that persists today. This transformation constitutes the last major phase change the universe has experienced, the final transition in the thermal history of cosmic matter. Reionization left observable traces that astronomers can detect today. The ionized plasma scattered the cosmic microwave background radiation, leaving subtle imprints that advanced instruments can measure. Additionally, the process affected the light from the earliest quasars, extraordinarily bright objects powered by supermassive black holes. By studying how this light is absorbed by intervening hydrogen, astronomers can map the progression of reionization across cosmic history. While the first stars formed in isolation or small clusters, they soon became the building blocks for more complex structures. As dark matter halos merged under gravity's influence, their stellar components combined as well. The first galaxies began to assemble approximately 300 to 500 million years after the Big Bang. Collections of stars held together by gravity and embedded within larger halos of dark matter. These proto-galaxies were much smaller and more irregular than modern galaxies like our Milky Way, typically containing perhaps 1 million to 1 billion stars. Compared to the hundreds of billions in today's large galaxies, they were cosmic embryos, the seeds from which larger structures would grow. They often exhibited chaotic, asymmetric shapes, as they had not yet settled into the ordered disks or elliptical forms common in the present-day universe. Within these early galaxies, new generations of stars were born. Unlike the first population, the 3 stars that formed from pristine hydrogen and helium, these new stars incorporated some of the heavy elements produced by their predecessors. Astronomers call these second-generation stars population 2 stars. While still metal-poor by modern standards, these stars could form with a wider range of masses, including some smaller, cooler stars that might still exist today in the oldest parts of our galaxy. The formation of population 2 stars marked another significant shift in cosmic evolution. With metals now present in the interstellar medium, gas could cool more efficiently. This enhanced cooling allowed gas clouds to fragment into smaller clumps, enabling the formation of less massive stars. Some of these stars were small enough to still be shining today, nearly 14 billion years later. Indeed, astronomers have identified ancient stars in our galaxy's halo that appear to be survivors from this early era, living fossils from the dawn of stellar evolution. As these early galaxies evolved, they began to interact and merge. Computer simulations reveal a hierarchical process of structure formation, with smaller galaxies combining to form larger ones. This process of galactic cannibalism continues today, though at a much slower pace. The earliest galaxies were closer together in the smaller, denser early universe, making collisions and mergers more frequent and dramatic than in the present epoch. Hubble Space Telescope observations have revealed some of these early galaxies as faint, red smudges in deep field images. The light from these ancient systems has been traveling for over 13 billion years, stretched by cosmic expansion from ultraviolet and visible wavelengths into the infrared. The James Webb Space Telescope, with its superior infrared capabilities, is designed specifically to observe these first galaxies in greater detail, potentially revolutionizing our understanding of this formative period. The first galaxies were not evenly distributed throughout space. Instead, they traced the underlying cosmic web, the network of filaments and nodes formed by dark matter. Proto-galaxies emerged preferentially at the intersections of these filaments, where the density of both dark and ordinary matter was highest. This pattern established the large-scale structure of the universe that persists today, with galaxies clustered along filaments surrounding relative voids, a cosmic architecture that resembles a sponge or foam when mapped in 3 dimensions. Within the first billion years after the Big Bang, another extraordinary phenomenon emerged: the first quasars. These objects, the most luminous sustained sources of electromagnetic radiation in the universe, are powered by supermassive black holes actively consuming surrounding matter. The discovery of quasars dating to less than a billion years after the Big Bang presents a cosmic puzzle. How did black holes with masses of billions of suns form so quickly? Several mechanisms have been proposed. Perhaps the first stars, significantly more massive than modern stars, collapsed directly into substantial black holes. These seed black holes might then have grown rapidly by consuming the abundant gas in the early universe. Alternatively, direct collapse of massive gas clouds might have formed black holes with initial masses of tens of thousands of suns, providing a head start for growth. Whatever the mechanism, these early supermassive black holes became the central engines for quasars, which in turn played important roles in galactic evolution and cosmic reionization. The intense radiation and energetic outflows from these early quasars likely influenced their host galaxies significantly, potentially regulating star formation by heating or expelling gas. This feedback process exemplifies the complex interplay between different components in the evolving cosmos. From the very beginning, galaxies were not simply collections of independent stars, but interactive systems where stellar formation, supermassive black holes, and gas dynamics affected one another in intricate ways. By approximately 1 billion years after the Big Bang, the basic elements of the modern universe were in place. Stars of various masses shone throughout the cosmos. Galaxies in various stages of evolution populated the nodes and filaments of the cosmic web. Heavy elements, though still less abundant than today, had begun enriching the interstellar and intergalactic medium, and the universe had become largely transparent to ultraviolet light following the completion of reionization. Yet this early universe differed dramatically from our current cosmic environment. Star formation occurred at much higher rates, driven by the abundant gas available in young galaxies. Collisions and mergers between galaxies were more common in the smaller, denser universe, and the cosmic landscape continued to evolve rapidly as hierarchical structure formation proceeded, with smaller objects merging to form larger ones. One remarkable aspect of this era is how quickly complexity emerged from simplicity. In just a billion years, about 7% of the universe's current age, the cosmos transformed from a relatively uniform distribution of neutral hydrogen and helium into a rich ecosystem of stars, galaxies, and heavy elements. The foundations for all future cosmic structure, including the potential for life, were established during this relatively brief but extraordinarily fertile period. The transformation was not just physical but chemical. Before the first stars, the periodic table effectively ended at lithium, element 3. After a billion years of stellar alchemy, elements like carbon, nitrogen, oxygen, silicon, and iron had become widespread, though still less abundant than in the modern universe. This chemical enrichment set the stage for later formation of rocky planets, complex molecules, and eventually, life. The light from the first stars and galaxies takes us to the frontier of current observational capabilities. Until recently, this era remained largely inaccessible to direct observation, known primarily through theoretical models and computer simulations. But advanced telescopes, particularly those optimized for infrared observation, like the James Webb Space Telescope, are beginning to provide glimpses of these early luminous objects, confirming some predictions and challenging others. What we're discovering is that galaxy formation may have begun earlier than previously thought. Recent observations have identified galaxy candidates from less than 400 million years after the Big Bang, earlier than many models predicted. These findings suggest that the transition from darkness to light might have proceeded more rapidly than astronomers had anticipated, with structure formation accelerating quickly once the first stars ignited. The first stars and galaxies also established patterns that would persist throughout cosmic history. The tendency of galaxies to form along filaments of dark matter, the regulation of star formation through various feedback mechanisms, the growth of supermassive black holes at galactic centers. All these fundamental processes were established during this formative period. The universe was developing the basic architecture and dynamics that would characterize it for billions of years to come. This era also witnessed the beginning of cosmic recycling. The death of the first stars released newly forged elements into space, enriching the gas from which subsequent stellar generations would form. This process of stellar birth, nucleosynthesis, death, and enrichment established a cosmic cycle that continues today. Every generation of stars incorporates the elements produced by previous generations, building upon the chemical legacy of its predecessors. The first galaxies were the nurseries for this process of cosmic enrichment. Within these early systems, successive generations of stars were born from increasingly metal-rich gas, accelerating the production of heavy elements. Galactic mergers mixed these enriched materials, spreading the products of stellar nucleosynthesis throughout the growing cosmic structures. The universe was becoming progressively more chemically diverse and complex. As we look out at the night sky today, we're witnessing the distant descendants of these first luminous objects. Our own Milky Way galaxy, though far larger and more structured than the first galaxies, grew from similar humble beginnings. The oldest stars in our galaxy's halo are survivors from this early epoch. Ancient Population 2, stars that formed when the universe was young, bearing witness to nearly 14 billion years of cosmic evolution. The journey from the first stars to our current universe was long and complex, involving countless stellar births and deaths, innumerable galactic mergers, and ongoing chemical enrichment. But the basic ingredients and processes were established during that first billion years, when light returned to the cosmos and complexity began to flourish. The universe had transitioned from its dark, simple beginnings to a luminous, structured state that would eventually enable the emergence of planets, life, and consciousness. Across the vast cosmic distances, the light from these first stars and galaxies carries information about conditions in the early universe. By studying this ancient light, astronomers can test theories of cosmic evolution, constrain models of dark matter and dark energy, and piece together the story of how our universe transformed from primordial simplicity to contemporary complexity. Each distant galaxy glimpsed from this era adds another data point to our understanding of cosmic dawn. As we continue our journey through cosmic history, we move forward in time from this era of first light to the formation of more mature cosmic structures, including our own Milky Way galaxy. The basic players in the cosmic drama have been introduced: stars, galaxies, black holes, and heavy elements. Now we'll explore how these components evolved and interacted over billions of years, ultimately creating the conditions necessary for our own existence. The lighting of the first stars and the formation of the first galaxies marked the end of cosmic prehistory and the beginning of the universe as we might recognize it. From a dark sea of neutral hydrogen and helium emerged points of brilliant light, sources of new elements, and the first complex structures held together by gravity. This transition, from darkness to light, from simplicity to complexity, represents one of the most significant chapters in our cosmic story, the moment when the universe first began to resemble the starlit cosmos we inhabit today. As the universe continued its expansion and evolution, the first small galaxies began to merge and grow into larger, more complex systems. Among these emerging structures was the embryonic form of our own cosmic home, the Milky Way. Approximately 12 to 13 billion years ago, just 1 to 2 billion years after the Big Bang, the foundations of our galaxy began to take shape within its massive dark matter halo. The story of our galaxy's formation is written in the stars themselves, particularly in the oldest stars found in the galactic halo, which surrounds the familiar spiral disk like a diffuse spherical cloud. These ancient stars, some nearly as old as the universe itself, contain chemical signatures that tell us about conditions in the early cosmos. They are cosmic fossils, preserving information about the environment in which they formed, much as paleontologists use dinosaur bones to reconstruct ancient Earth. Unlike the brilliant blue giants that first illuminated the cosmic darkness, many of these early population 2 stars were small enough to still be shining today, nearly 14 billion years later. By studying their composition, astronomers have determined that they formed from gas that had been only slightly enriched with heavy elements from the first generation of stars. Their existence and properties help us reconstruct the Milky Way's earliest days. Current models suggest that our galaxy formed through a process called hierarchical assembly, the gradual merger of many smaller proto-galaxies into a larger structure. This wasn't a single event, but an extended process that began in the cosmic dawn and continues, albeit at a much slower pace, to the present day. Our galaxy has consumed hundreds of smaller galaxies throughout its long history, incorporating their stars, gas, and dark matter into its growing form. Evidence for this cannibalistic history is found in stellar streams, ribbons of stars with similar properties flowing through the galactic halo. These streams are the tidal debris of small galaxies and star clusters torn apart by the Milky Way's gravitational pull. By identifying and mapping these stellar streams, astronomers can reconstruct past merger events, much as a detective might reconstruct a crime from scattered evidence. One of the most significant early chapters in our galaxy's formation likely involved the merger with a substantial galaxy astronomers have named Gaia Enceladus, sometimes called the Gaia sausage due to its elongated shape in velocity space. This cosmic collision, occurring approximately 8 to 11 billion years ago, may have delivered up to 50 billion stars to our growing galaxy, a substantial fraction of its mass at that time. The stars from this ancient merger still maintain distinguishable orbital patterns and chemical compositions, allowing astronomers to identify them among the Milky Way's stellar population. While these early mergers were shaping the galactic halo, another crucial structure was forming: the galactic disk. Approximately 10 billion years ago, gas began to settle into a rotating disk around the galaxy's center. As this gas cooled and condensed, it fragmented into clouds that gave birth to new generations of stars. Unlike the spherical distribution of the oldest stars in the halo, these new stars formed in a flattened disk due to the conservation of angular momentum, the same physical principle that causes a spinning ball of dough to flatten into a pizza shape. The disk that formed wasn't uniform, but developed a spiral structure. These magnificent spiral arms, visible in images of many galaxies throughout the universe, aren't solid structures but rather density waves, regions where gas and stars become temporarily concentrated, similar to how cars bunch up in a traffic jam. These density waves trigger star formation as they compress gas clouds, leading to the brilliant blue star-forming regions that trace spiral patterns in galaxies like our own. At the center of our growing galaxy, another critical structure was developing: the galactic bulge. This roughly spherical concentration of stars surrounding the galactic center formed through a combination of processes. Some stars were born directly from gas that rapidly collapsed toward the galactic center early in the Milky Way's history. Others were acquired through mergers with smaller galaxies, and some migrated inward from the disk due to gravitational interactions with other stars, gas clouds, and spiral arms. Within this central bulge lurks one of the galaxy's most enigmatic features: a supermassive black hole named Sagittarius A star. With a mass approximately 4 million times that of our Sun, this cosmic behemoth likely formed early in the galaxy's history, perhaps beginning as a smaller seed black hole that grew by consuming gas and stars, or through mergers with other black holes during galactic collisions. While modest compared to the most massive black holes in the universe, which can reach billions of solar masses, our galactic black hole has played an important role in shaping the central regions of the Milky Way. By approximately 8 billion years ago, the basic structure of our galaxy was established: a central bulge surrounded by a rotating disk, all embedded within a diffuse halo of older stars and dark matter. But the Milky Way continued to evolve. New stars formed from gas enriched by previous stellar generations, particularly in the disk. Successive waves of star formation created the distinct populations we observe today, each with chemical compositions reflecting the progressive enrichment of the interstellar medium. Astronomers can trace this chemical evolution through what they call galactic archaeology, the study of stellar populations and their elemental abundances. Much as an archaeologist might use artifacts to reconstruct human history, astronomers use the chemical compositions of stars as cosmic artifacts that reveal the galaxy's environmental conditions throughout its history. The oldest stars contain primarily hydrogen and helium, with just traces of heavier elements, while younger stars like our Sun incorporate substantial amounts of carbon, oxygen, and other elements produced by previous stellar generations. Our Milky Way galaxy didn't form in isolation, but as part of a growing cosmic neighborhood. The local group, as astronomers call our galactic neighborhood, consists of more than 50 galaxies bound together by gravity, dominated by two major spiral systems, our Milky Way and the slightly larger Andromeda Galaxy, M31, located approximately 2.5 million light-years from us. The remaining members are primarily dwarf galaxies, many of which orbit as satellites around these two giants. The third largest member of the local group is the Triangulum Galaxy, M33, another spiral galaxy somewhat smaller than the Milky Way, together with Andromeda and numerous dwarf galaxies. These systems form a gravitationally bound collection of galaxies that will ultimately merge in the distant future. Astronomers project that the Milky Way and Andromeda will collide and merge approximately 4.5 billion years from now, forming a single, larger elliptical galaxy sometimes called Milkomeda. Among the Milky Way's current satellite galaxies, the most prominent are the Large and Small Magellanic Clouds, visible as fuzzy patches in the southern hemisphere sky. These irregular dwarf galaxies orbit our galaxy at distances of approximately 160,000 and 200,000 light-years, respectively. They are currently being distorted by the Milky Way's gravitational pull, which is stripping away gas and stars to form the Magellanic Stream, a long trail of gas extending more than 100 degrees across the sky. The Sagittarius Dwarf elliptical galaxy represents another ongoing merger, being currently torn apart as it passes through the disk of our galaxy. First discovered in 1994, this small galaxy has orbited the Milky Way several times, each passage stripping away more of its stars to form a prominent stellar stream. After several more orbits, it will be completely absorbed, another meal in our galaxy's long history of cosmic cannibalism. Beyond the local group lies a much larger structure known as the Virgo supercluster, a collection of galaxy groups and clusters spanning approximately 110 million light-years. This vast assembly contains thousands of galaxies, including many larger and more massive than our Milky Way. And beyond this supercluster lies an even grander structure, the Laniakea supercluster, a gigantic complex of galaxies that includes the Virgo supercluster as just one component. These nested structures, from our solar system to the Milky Way, the local group, the Virgo supercluster, and Laniakea, reflect the hierarchical nature of cosmic organization. Each level emerges from the clustering of smaller components under the influence of gravity, tracing patterns established in the universe's earliest eras. The large-scale distribution of these structures follows the cosmic web first mapped out by dark matter shortly after the Big Bang, with clusters and superclusters forming at the nodes where filaments of this web intersect. The formation and evolution of galaxies like our Milky Way has been strongly influenced by dark matter, that mysterious substance that neither emits nor absorbs light, but exerts gravitational pull. The Milky Way's dark matter halo, extending far beyond the visible disk of stars, contains approximately 5 to 10 times more mass than all the visible matter combined. This invisible component provided the gravitational scaffolding around which our galaxy formed and continues to influence its dynamics today. Another invisible component that has shaped galactic evolution is dark energy, the mysterious force causing the universe's expansion to accelerate. While dark matter pulls matter together to form structures, dark energy pushes space itself apart, affecting cosmic evolution on the largest scales. As the universe expands at an ever-increasing rate, distant galaxy clusters recede from one another, becoming increasingly isolated. In the far future, These effects will dramatically alter the cosmic landscape, potentially leaving each galaxy cluster as an island universe, disconnected from the broader cosmic web. The evolution of our Milky Way has not proceeded at a constant pace, but rather through episodes of more and less intense activity. Evidence suggests that approximately 6 billion years ago, the galaxy experienced a significant burst of star formation, possibly triggered by a merger with a gas-rich satellite galaxy. This period, sometimes called the thick disk formation phase, produced many of the somewhat older stars found in the thicker component of our galactic disk. Another key phase in the Milky Way's evolution occurred approximately 4.6 billion years ago, the formation of our own solar system. While not significant on galactic scales, this event produced the only planetary system we know with absolute certainty to harbor life. The Sun and planets formed from a collapsing cloud of gas and dust enriched by multiple generations of previous stars, incorporating elements forged in stellar furnaces and supernova explosions billions of years earlier. The Milky Way continues to evolve today. Stars are still forming, primarily in the spiral arms of the galactic disk, at a rate of approximately 1 to 2 solar masses per year. Modest compared to the most active star-forming galaxies, but sufficient to keep our galaxy vibrant. Gas continues to accrete onto the galaxy from the intergalactic medium and from the Magellanic Clouds, providing fuel for future stellar generations. As we observe other galaxies throughout the universe, we see systems in various stages of evolution, allowing us to piece together a more complete picture of galactic development. Some galaxies resemble what our Milky Way might have looked like billions of years ago. Active, somewhat chaotic systems with high rates of star formation. Others represent possible futures for our galaxy. Massive elliptical galaxies form through the merger of multiple spiral systems, where star formation has largely ceased, and older, redder stars dominate. The diversity of galaxies across the cosmos is astonishing. Spiral galaxies like our own, with their graceful arms winding outward from a central bulge, represent just one galactic morphology. Elliptical galaxies range from giant systems containing trillions of stars to dwarf ellipticals with just a few million. Irregular galaxies show little organized structure, often due to gravitational interactions with neighbors. And some active galaxies harbor central black holes that consume matter at tremendous rates, producing jets and outflows visible across billions of light years. This variety reflects different formation histories and environmental influences. Galaxies in dense cluster environments tend to evolve differently from those in more isolated regions. Those that experienced many major mergers often become elliptical, losing their disk structure in the process. Those that grew primarily by accreting gas and smaller satellites, like our Milky Way, tend to maintain their spiral patterns. And those currently interacting with neighbors often display irregular features, tidal tails, bridges of stars, and gas stretching between systems, and enhanced star formation triggered by gravitational compression of gas clouds. Recent observations have revealed that our local cosmic neighborhood is part of a much larger structure called the Laniakea supercluster, meaning immense heaven in Hawaiian. This vast complex, spanning more than 500 million light-years, contains approximately 100,000 galaxies with a total mass of 100 quadrillion, 100,000 billion suns. Our Milky Way resides in a relatively quiet suburb of this enormous cosmic metropolis, in a low-density region between major filaments of the cosmic web. This positioning has likely influenced our galaxy's evolution and possibly even the emergence of life. Had the Milky Way formed in a denser cluster environment, more frequent galactic encounters might have disrupted the relatively stable conditions that allowed complex life to evolve on Earth. Our cosmic address, in a mid-sized galaxy, in a relatively quiet region of a supercluster, may be one factor that enabled our existence as conscious observers of the universe. As astronomers peer deeper into space and further back in time, they continue to refine models of galactic formation and evolution. The James Webb Space Telescope, with its unprecedented infrared sensitivity, is designed to observe the earliest galaxies, potentially revolutionizing our understanding of how these cosmic structures first assembled. Other instruments like the Gaia spacecraft are mapping the positions and motions of billions of stars within our own galaxy, allowing us to reconstruct its formation history with unprecedented detail. What's emerging from these investigations is a picture of galaxies as dynamic, evolving systems, not static structures, but rather processes unfolding over billions of years. Our Milky Way has transformed dramatically since its earliest progenitors formed in the cosmic dawn. It has grown through mergers, developed its spiral structure, experienced waves of star formation, and continued to accrete material from its surroundings. And this evolution continues today, with future mergers, particularly with the approaching Andromeda Galaxy, guaranteed to transform it yet again. The story of the Milky Way and its cosmic neighborhood connects us directly to the broader narrative of cosmic evolution. The atoms in our bodies were forged in stars that lived and died within our galaxy. The elements essential for life, carbon, nitrogen, oxygen, phosphorus, and others, were produced through stellar nucleosynthesis and scattered through the interstellar medium by supernova explosions. Later generations of stars, including our Sun, incorporated these elements, making possible the emergence of planets and eventually life. In this sense, we are not merely observers of galactic evolution, but products of it. Stardust organized into complex forms, capable of contemplating the very processes that made our existence possible. The Milky Way is not just our home, but our parent, the system whose 13 billion-year history of star formation, chemical enrichment, and structural evolution created the conditions necessary for conscious beings to evolve on at least one small planet orbiting an ordinary star. As we continue our cosmic journey, we turn our attention from the grand scale of galaxies to the more intimate environment of our solar system. Here, in our local cosmic neighborhood, another chapter of the universe's evolution unfolded, the formation of a star and its family of planets, including the small rocky world, where consciousness would eventually emerge to contemplate the cosmos. Approximately 4.6 billion years ago, in an unremarkable spiral arm of the Milky Way galaxy, a vast cloud of gas and dust began to collapse under its own gravity. This molecular cloud, composed of material recycled from previous generations of stars, contained all the ingredients necessary for a new star system. Within this swirling maelstrom of matter, our solar system would be born, a star surrounded by planets, moons, asteroids, and comets, including the small rocky world that would eventually become home to conscious life. The story of our solar system's birth is written in the planets, moons, and countless smaller bodies that orbit the Sun today. By studying their compositions, orbits, and physical characteristics, scientists have reconstructed the dramatic sequence of events that transformed a diffuse nebula into the complex planetary system we inhabit. This cosmic origin story reveals both the commonality of processes that likely form planetary systems throughout the universe, and the particular circumstances that made our system, especially Earth, a haven for life. The molecular cloud that would become our solar system was itself the product of billions of years of cosmic evolution. Unlike the primordial gas that emerged from the Big Bang, composed almost entirely of hydrogen and helium, this cloud contained significant quantities of heavier elements, what astronomers call metals: carbon, oxygen, silicon, iron, and countless other elements forged in the nuclear furnaces of previous stellar generations and scattered through space by supernovae, had been incorporated into this gigantic cloud. The trigger for this cloud's collapse remains uncertain. Perhaps the shockwave from a nearby supernova compressed the gas beyond its stability threshold, or maybe the cloud passed through a particularly dense spiral arm of the galaxy, experiencing extra gravitational compression. Whatever the initial cause, once collapse began, gravity amplified the process. As the cloud contracted, it began to spin faster, like an ice skater pulling in their arms during a spin, a consequence of the conservation of angular momentum. This rotation caused the collapsing cloud to flatten into a spinning disk, with most of the mass concentrating in the center where pressure and temperature steadily increased. This central condensation would become our Sun, while the surrounding disk, called a protoplanetary disk or solar nebula, provided the material from which the planets would form. This disk likely spanned hundreds of astronomical units, one astronomical unit being the distance from Earth to the Sun, about 150 million kilometers. As the central protostar accumulated more mass, its core grew increasingly hot and dense. When the temperature reached approximately 15 million degrees Kelvin, nuclear fusion ignited. Hydrogen atoms began combining to form helium, releasing enormous energy in the process. With this momentous event, approximately 4.6 billion years ago, our Sun was born, a self-sustaining fusion reactor that would provide light and heat to its developing planetary system for billions of years to come. The young Sun was more volatile than the stable star we orbit today. It likely rotated more rapidly and emitted more intense solar flares and coronal mass ejections. It also produced a stronger solar wind, a stream of charged particles that would help clear the inner solar system of excess gas. This energetic young star had a profound influence on the developing planetary system, particularly on the chemistry and dynamics of the inner regions of the protoplanetary disk. Meanwhile, in the disk surrounding this nascent star, the process of planet formation was underway. The first step involved the condensation of solid particles from the gas. In the hot inner regions of the disk, only materials with high melting points, primarily metals and silicates, rocky materials, could condense into solid form. Further out, beyond what astronomers call the frost line or snow line, the cooler temperatures allowed volatile substances like water, methane, and ammonia to freeze into solid ice particles. This temperature gradient established a fundamental division that would shape our solar system. Rocky planets would form in the inner regions, while gas giants and ice-rich bodies would dominate the outer regions. The next stage in planet formation involved these tiny solid particles, dust grains and ice crystals, sticking together to form progressively larger aggregates. Through gentle collisions within the disk, these particles grew from microscopic specks to pebble-sized objects. As they grew larger, their interactions became more complex. Some collisions resulted in fragmentation rather than growth, while others led to further accretion. Gradually, through countless interactions, these materials formed kilometer-sized objects called planetesimals, the building blocks of planets. The story of the universe is ongoing. Each scientific discovery refines our understanding, sometimes dramatically revising previous chapters of our cosmic narrative. What we present here represents our best current knowledge, but future generations will surely uncover deeper truths and correct our inevitable mistakes. This provisional quality doesn't undermine the value of our current understanding. It exemplifies the self-correcting nature of the scientific process that has brought us this far. To understand the universe, we must start at the very beginning, or even before it. What existed before the Big Bang? Was there a before at all? These questions push the boundaries of both science and philosophy. Some theories suggest our universe emerged from a quantum fluctuation in a pre-existing state. Others propose a cyclic cosmos, eternally expanding and contracting. Still others suggest multiple universes bubbling into existence, with ours being just one among countless others. These ideas challenge not just our understanding of physics, but our very notion of what constitutes an explanation. When we ask about conditions before time began, we may be posing a fundamentally incoherent question, like asking what's north of the North Pole. Yet, science continues to probe these profound boundaries, seeking mathematical models that might connect our observable universe with its deepest origins. As we embark on this cosmic journey together, we invite you to embrace both the knowledge we've gained and the mysteries that remain. The history of the universe is your history. The atoms in your body have existed since shortly after the Big Bang. They have been part of stars, interstellar clouds, and perhaps other worlds before becoming part of you. In a very real sense, you are the universe becoming conscious of itself, stardust that has learned to wonder about its origins. So join us as we travel back to the beginning of everything, to witness the greatest story ever told. A tale of how hydrogen atoms, given 13.8 billion years, transformed themselves into human beings capable of contemplating the very stars that forge the elements from which we are made. This is not merely a scientific chronicle, it is our collective autobiography, the story of us, written in the language of space and time. These planetesimals then underwent a process called runaway accretion. The largest objects, with their stronger gravitational pull, grew faster than their smaller counterparts, accumulating more material and growing even larger. This snowball effect led to the formation of moon-sized to Mars-sized bodies called planetary embryos or protoplanets. In the inner solar system, dozens of these protoplanets likely formed within the first few million years. What followed was a period of chaotic interactions that astronomers call the late heavy bombardment or the terminal cataclysm. These protoplanets didn't orbit in the neat, well-spaced patterns we see today. Instead, they followed more erratic paths that frequently brought them close to one another. Gravitational interactions changed their orbits, leading to frequent collisions. Some protoplanets merged to form larger bodies. Others were shattered, their fragments becoming asteroids or meteoroids, and some were ejected from the solar system entirely or fell into the sun. One such collision had particularly profound consequences for our planet. Approximately 4.5 billion years ago, a Mars-sized protoplanet that scientists have named Theia collided with the early Earth. This wasn't a head-on impact, but rather an oblique collision. Much of Theia's mass merged with Earth, significantly increasing its size. Meanwhile, debris from the collision was ejected into orbit around Earth, where it eventually coalesced to form the Moon. This dramatic origin explains several peculiar features of the Earth-Moon system. It accounts for the Moon's unusually large size relative to its planet. No other rocky planet in our solar system has such a proportionally massive satellite. It explains why the Moon has a composition similar to Earth's mantle, but lacks a substantial iron core. The core materials of Earth and Theia had already sunk to their respective centers before the collision. And it explains why Earth has a relatively high rate of rotation and the Moon orbits in the same plane as Earth's equator. Beyond its role in forming the Moon, this giant impact had other significant consequences for Earth's development. The tremendous energy of the collision would have melted much of our planet, creating a global magma ocean. This facilitated the differentiation of Earth's interior into distinct layers: a metal core, silicate mantle, and eventually a solid crust. The impact may also have delivered additional volatile materials to Earth and influenced the tilt of our planet's rotational axis, which is responsible for our seasons. While the rocky inner planets were forming through these violent processes, a different mechanism was at work in the outer solar system. Beyond the frost line, protoplanets grew much larger due to the abundance of solid ices. Once they reached a critical mass, approximately 10 Earth masses, they became massive enough to capture and retain hydrogen and helium gas directly from the solar nebula. This process gave birth to the gas giants, Jupiter and Saturn. Jupiter, as the largest and first to form, had a particularly profound influence on the developing solar system. Its powerful gravitational field affected the orbits of nearby bodies, preventing the formation of a single planet in what is now the asteroid belt between Mars and Jupiter. Instead, this region remains populated by numerous small bodies, asteroids, that represent leftover building blocks from the planet formation process. Farther out, Uranus and Neptune formed through a similar process, but with a crucial difference. By the time these planets grew large enough to accrete significant gas, much of the hydrogen and helium in the solar nebula had been cleared away by the solar wind or captured by Jupiter and Saturn. As a result, these planets incorporated proportionally more ices and fewer light gases, becoming what astronomers call ice giants rather than gas giants. Beyond the orbit of Neptune, the disk was too sparse for large planets to form. Instead, this region gave rise to countless smaller icy bodies, including Pluto and similar dwarf planets, as well as the myriad smaller objects of the Kuiper Belt. Even farther out, extending to nearly a light year from the Sun, lies the Oort Cloud. a spherical shell of icy bodies that occasionally become visible as long-period comets when perturbed into the inner solar system. The formation of our solar system wasn't a neat, orderly process, but rather a dynamic and at times violent sequence of events. The planets didn't form in their current locations and orbits. Instead, substantial migration occurred, with giant planets likely moving inward and then outward again through interactions with the disk and with each other. One model, called the Nice model, named after the city in France where it was developed, suggests that the giant planets formed in a much more compact configuration before spreading to their current orbits, causing significant disruption throughout the solar system in the process. This planetary migration had profound effects on the smaller bodies of the solar system. As Jupiter moved outward, it swept material into the asteroid belt and potentially drove water-rich asteroids into the inner solar system, where they could deliver water to the terrestrial planets. The migration of Neptune is thought to have scattered countless icy objects outward, forming the current Kuiper Belt and sending some bodies all the way to the distant Oort Cloud. Others were directed inward, contributing to a period of intense bombardment of the inner solar system approximately 4 billion years ago. This late heavy bombardment left its mark most visibly on the Moon, whose ancient highlands are covered with overlapping impact craters dating from this era. Mercury, Mars, and Earth were similarly affected, though Earth's active geology and weathering have erased most evidence of these ancient impacts. This bombardment wasn't merely destructive, however. The impacting asteroids and comets likely delivered additional water and organic compounds to Earth, potentially providing important ingredients for the later development of life. By approximately 4 billion years ago, the major dynamic events of solar system formation had concluded. The planets had settled into stable orbits, clearing their paths of most smaller objects. The debris disk had dissipated, with remaining small bodies concentrated in the asteroid belt, Kuiper Belt, and distant Oort Cloud. The Sun had entered its main sequence phase, the stable middle-aged state in which we observe it today. Our solar system had taken on a form broadly similar to its current configuration, yet the story was far from over. On at least one planet, Earth, conditions were conducive for another kind of evolution. With its substantial size, moderating moon, liquid water oceans, and diverse chemistry enriched by asteroid and comet impacts, Earth provided an environment where life could emerge. Approximately 3.8 to 3.5 billion years ago, the first simple organisms appeared, beginning a process of biological evolution that would eventually lead to humans, beings capable of reconstructing this cosmic history. The other planets followed different evolutionary paths. Venus, similar in size to Earth but slightly closer to the Sun, experienced a runaway greenhouse effect that transformed it into the scorching, high-pressure inferno we observe today. Mars, smaller and farther from the Sun, started with liquid water and perhaps even primitive life, but gradually lost most of its atmosphere and surface water as its core cooled and its protective magnetic field faded. Jupiter and the other giant planets, composed primarily of light gases, experienced less dramatic changes, though their complex weather systems and relationships with their many moons continue to evolve. The formation of our solar system illustrates processes that likely occur throughout the universe. Since 1995, astronomers have discovered thousands of planets orbiting other stars, exoplanets, revealing a startling diversity of planetary systems. Some contain hot Jupiters, gas giants orbiting extremely close to their stars. Others feature super-Earths, or mini-Neptunes, planet types that don't exist in our solar system. Some stars host tightly packed systems of multiple planets. Others have planets on highly elliptical orbits, or even circling in directions opposite to their star's rotation. This diversity suggests that planet formation is a complex process with many possible outcomes. The particular architecture of our solar system, small rocky planets in the inner regions, large gas giants in the middle zones, and smaller icy bodies in the outer reaches, represents just one possible configuration. The specific conditions of the molecular cloud, the properties of our Sun, and perhaps some degree of chance contributed to creating the particular system we inhabit. Yet within this diversity, patterns emerge. Many of the exoplanetary systems discovered to date include multiple planets, suggesting that planet formation typically produces families of worlds rather than isolated objects. Many contain planets that migrated from their formation locations, indicating that the dynamic rearrangement observed in our solar system is common. And recent discoveries suggest that Earth-sized planets in potentially habitable orbits may be relatively common around red dwarf stars, the most numerous stellar type in our galaxy. From these observations, a picture emerges of our solar system as neither uniquely special nor entirely ordinary. Its architecture differs from many observed exoplanetary systems, yet the processes that formed it appear to operate throughout the galaxy. Its history of dynamic interactions, migrations, and bombardments reflects common aspects of planet formation. And while Earth remains the only world known with certainty to harbor life, the ingredients and conditions that enabled life here, water, organic chemistry, energy sources, and stable environments, likely exist in various combinations elsewhere. The study of our solar system's formation continues to advance through multiple avenues of investigation. Space missions to asteroids and comets, pristine leftovers from the formation era, provide direct samples of early solar system materials. Observations of protoplanetary disks around young stars offer glimpses of planetary systems in the process of formation, and sophisticated computer models, incorporating physics from the subatomic to the galactic scale, simulate the complex interactions that transform diffuse clouds into ordered planetary systems. What emerges from these investigations is a narrative connecting our solar system's birth to both the broader cosmic processes we've traced throughout this journey and the specific conditions that enabled life on Earth. Our planetary system formed from materials recycled through multiple generations of stars, incorporating elements forged in stellar furnaces and supernova explosions. Its architecture resulted from universal physical laws acting under particular initial conditions, and its subsequent evolution created at least one world where life could take hold and eventually develop the consciousness necessary to contemplate these cosmic origins. As we continue our journey through cosmic history, we turn next to one of the most extraordinary chapters in this grand narrative, the emergence of life on Earth. From simple organic chemistry to complex, self-aware organisms capable of studying their own origins, life represents another transformation in cosmic complexity. Just as hydrogen atoms formed stars, and stars forged the elements necessary for planets, those planets, in at least one case, provided environments where matter could organize itself into increasingly complex, self-replicating forms, eventually developing the capacity to understand the universe that created it. Approximately 3.8 to 3.5 billion years ago, on the young planet Earth, something extraordinary happened. From the interplay of simple molecules in primordial waters emerged the first self-replicating systems, the earliest forms of life. This transition from non-living chemistry to living biology represents one of the most profound transformations in cosmic history. For the first time in our planet's existence, and perhaps for the first time in our region of the galaxy, matter had organized itself into entities capable of reproduction, metabolism, and evolution. The universe had taken the first step toward becoming aware of itself. The emergence of life on Earth connects the cosmic story we've been tracing, from the Big Bang through star formation, galactic evolution, and the birth of our solar system, to the biological realm that would eventually produce conscious observers capable of contemplating this grand narrative. Understanding how non-living matter transformed into living systems represents both one of science's greatest challenges and one of its most profound frontiers. The young Earth where life emerged was dramatically different from the planet we inhabit today. After its formation approximately 4.5 billion years ago, our world was a hot, volcanically active environment with little free oxygen in its atmosphere. The primordial atmosphere likely contained nitrogen, carbon dioxide, water vapor, and various volcanic gases like hydrogen sulfide and sulfur dioxide. Meteorites and comets continue to impact the surface, delivering additional water, organic compounds, and energy to the developing planet. Electrical storms frequently illuminated the skies, while intense ultraviolet radiation from the young sun reached the surface unfiltered by the ozone layer that would later form. In this apparently hostile setting, the chemical precursors of life began to accumulate. Carbon-based molecules, hydrocarbons, alcohols, acids, and more complex structures formed in the atmosphere, on the planet's surface, and in its waters. These molecules weren't alive, but they were the building blocks from which life would emerge. Some of these compounds arrived via meteorites and comets, which analysis has shown contain amino acids, nucleobases, and other organic materials. Others formed directly on Earth through reactions energized by lightning, ultraviolet radiation, or heat from hydrothermal systems. Scientists have proposed various environments where life might have first emerged. Traditional models suggest shallow pools near shorelines, where cycles of wetting and drying could concentrate organic compounds and catalyze critical reactions. More recent theories point to deep-sea hydrothermal vents, both the high-temperature black smokers and the more moderate alkaline vents, where chemical and thermal gradients could provide energy for primitive metabolic reactions. Others suggest that life might have started in geothermal pools, similar to those found in Yellowstone National Park today, where heat and mineral-rich waters create favorable conditions for complex chemistry. Regardless of the specific location, the pathway from non-living chemistry to the first cells required several crucial developments. One was the formation of polymers, long molecules composed of repeated subunits. The most important biological polymers include proteins, made from amino acids, nucleic acids like RNA and DNA, made from nucleotides, and in some cases, complex carbohydrates. Under primitive Earth conditions, forming these polymers presented challenges, as they tend to break down in water. However, minerals could have served as templates or catalysts, while cycles of wetting and drying or the concentration effects at air-water interfaces might have facilitated these crucial polymerization reactions. Another critical development was the emergence of self-replicating molecules, chemical systems capable of making copies of themselves. RNA, ribonucleic acid, has emerged as a leading candidate for the first self-replicating system. Unlike DNA, which primarily stores information, some RNA molecules can both carry genetic information and catalyze chemical reactions. These catalytic RNAs, called ribozymes, can facilitate their own replication under certain conditions. This dual capability, combining information storage with catalytic function, has led many scientists to propose an RNA world as an early stage in life's development, preceding the DNA-protein world that characterizes modern cells. Perhaps the most significant innovation was the development of compartmentalization, the separation of primitive biochemical systems from their surroundings by some form of membrane. Certain molecules called lipids naturally form hollow spheres in water, creating membrane-bound compartments similar to modern cells. These primitive membranes would have allowed early biochemical systems to concentrate their components, maintain chemical gradients, and evolve as distinct units. When these membrane-bound compartments incorporated self-replicating molecules and energy-harvesting systems, the first cell-like entities, protocells, could have emerged. The transition from complex chemical systems to true living cells represented a critical threshold. While we cannot pinpoint the exact moment or mechanism of this transition, living systems share certain fundamental properties. They maintain themselves away from thermodynamic equilibrium by harnessing energy from their environment. They reproduce, passing information to subsequent generations, and they evolve through natural selection, with variations in their structure leading to differential survival and reproduction. Evidence for early life on Earth comes from several sources. Microscopic structures resembling fossilized bacteria have been found in rocks dating back approximately 3.5 billion years. Chemical signatures of biological processes, including carbon isotope ratios characteristic of metabolism, appear in rocks of similar age. And genetic analyses of modern organisms allow scientists to reconstruct aspects of the universal common ancestor from which all current life descends, providing indirect glimpses of early biological systems. Once established, life began to diversify and evolve through natural selection, the process whereby organisms better adapted to their environment tend to survive and produce more offspring. The earliest organisms were likely prokaryotes, single-celled organisms without nuclei, similar to modern bacteria and archaea. These microbes probably obtained energy through various chemical reactions, including possibly using hydrogen, sulfur compounds, or simple organic molecules as fuel sources. Photosynthesis, the process of capturing energy from sunlight, evolved relatively early, but initially in forms that did not produce oxygen. A critical transition occurred approximately 2.4 to 2.7 billion years ago with the evolution of oxygenic photosynthesis, the ability to split water molecules using sunlight's energy, producing oxygen as a byproduct. This innovation, developed by ancestors of modern cyanobacteria, would dramatically transform Earth's atmosphere and oceans through what scientists call the Great Oxygenation Event. As photosynthetic organisms proliferated, oxygen levels began to rise, creating a crisis for many existing life forms that had evolved in an oxygen-poor environment. This oxygen, toxic to many primitive organisms, represented both an evolutionary challenge and opportunity. The rise of atmospheric oxygen had profound consequences. It enabled the evolution of more energy-efficient metabolic processes, as oxygen-based respiration yields substantially more energy than anaerobic alternatives. It led to the formation of the ozone layer, which shields the planet's surface from harmful ultraviolet radiation and allowed life to colonize land environments. And it created conditions favorable for the evolution of more complex multicellular organisms. The next major evolutionary innovation came with the emergence of eukaryotic cells, complex cells containing nuclei and specialized internal structures called organelles. Evidence suggests that eukaryotes arose through endosymbiosis, a process where one cell engulfed but did not digest another, resulting in a mutually beneficial partnership. Mitochondria, the energy-generating organelles in most eukaryotic cells, likely originated as free-living bacteria that were incorporated into larger cells. Similarly, chloroplasts, the photosynthetic organelles in plants and algae, derived from engulfed cyanobacteria. This fusion of once independent organisms created cells with unprecedented functional complexity. With the evolution of eukaryotic cells approximately 2 billion years ago, the stage was set for another major transition, the development of multicellular life. While simple colonial arrangements of cells had likely existed earlier, true multicellularity involves cells with different specialized functions working together as a single organism. This arrangement allows for larger size, more complex structure, and division of labor among specialized tissues and organs. The fossil record shows a dramatic diversification of multicellular life, beginning around 600 million years ago in an event called the Cambrian explosion. Within a relatively short geological timespan, most major animal body plans appeared, including ancestors of modern arthropods, mollusks, echinoderms, and chordates, the group that includes vertebrates. This extraordinary period of innovation established the foundation for the diverse animal life that would later evolve. The colonization of land represented another critical frontier. Plants, fungi, and animals began moving from aquatic environments to terrestrial ones approximately 450 million years ago. This transition required numerous adaptations, methods to prevent water loss, structural support against gravity, and reproductive strategies that didn't require external water. The greening of the continents transformed the planet's surface, accelerated weathering processes, altered atmospheric composition, and created new ecological niches. Throughout these evolutionary developments, life continuously shaped and was shaped by Earth's environmental conditions in a complex feedback system. Living organisms altered the atmosphere's composition, influenced the carbon cycle, weathered rocks, created soils, and modified local and eventually global climatic conditions. This interplay between life and its planetary environment, sometimes described by the Gaia hypothesis, demonstrates how biological processes became integral components of Earth's biogeochemical systems. The evolutionary journey continued with the rise and fall of successive groups of organisms. Fish diversified in the oceans, amphibians ventured onto land, reptiles evolved adaptations allowing complete independence from aquatic environments. Mammals developed hair and homeothermy, warm-bloodedness. Birds evolved feathers and flight. Flowering plants transformed terrestrial ecosystems. Each innovation opened new evolutionary possibilities, while often creating challenges for existing life forms. Periodic mass extinctions punctuated this evolutionary narrative, eliminating large percentages of species and reshaping Earth's biosphere. The most severe, the Permian-Triassic extinction approximately 252 million years ago, eliminated about 90% of marine species and 70% of terrestrial vertebrate species. These extinction events, triggered by various phenomena including volcanic eruptions, climate changes, and asteroid impacts, created opportunities for surviving lineages to diversify into vacant ecological niches. The most recent major extinction event, the Cretaceous-Paleogene extinction approximately 66 million years ago, was likely caused primarily by an asteroid impact at what is now the Yucatan Peninsula in Mexico. This catastrophe eliminated approximately 75% of species, including most dinosaurs. The mammals that survived this event subsequently diversified into numerous forms, including primates, the group that would eventually include humans. The emergence of the human lineage represents another profound transition in life's history. Approximately 6 to 7 million years ago, the lineage that would lead to humans diverged from the one leading to chimpanzees and bonobos, our closest living relatives. Over millions of years, our ancestors evolved bipedal locomotion, increased brain size, and enhanced cognitive capabilities. Approximately 300,000 years ago, anatomically modern humans, Homo sapiens, appeared, possessing unprecedented capabilities for language, abstract thought, technological innovation, and cultural transmission of knowledge. With the evolution of human consciousness, the universe achieved something remarkable: the capacity to contemplate its own existence through science, art, philosophy, and other forms of inquiry. Humans began systematically investigating the nature of reality, including both the cosmos that gave rise to them and their own inner experience. The atoms forged in stellar furnaces had organized themselves into beings capable of discovering those stellar origins and marveling at the cosmic processes that made their existence possible. This extraordinary capacity for self-reflection raises profound questions about the relationship between consciousness and the cosmos. Is conscious awareness an emergent property that naturally develops when matter achieves sufficient complexity under the right conditions? If so, has consciousness emerged elsewhere in the vast universe? Or is Earth's conscious life an exceptional rarity, the product of a highly improbable sequence of events unlikely to be repeated elsewhere? The question of whether life exists beyond Earth remains one of science's great unsolved mysteries. Within our solar system, several locations show potential for harboring at least simple life forms. Mars once had flowing water on its surface and might still support microbial life in subsurface environments. Europa and Enceladus, moons of Jupiter and Saturn respectively, contain vast subsurface oceans that could potentially host living organisms. And recent discoveries of thousands of exoplanets orbiting other stars, including many in potentially habitable zones, suggest that suitable environments for life might be common throughout the galaxy. If life has emerged independently elsewhere, its discovery would profoundly impact our understanding of cosmic evolution. It would suggest that the transition from non-living chemistry to biology, a occurs relatively readily under suitable conditions, making life a common feature of the universe rather than an exceptional rarity. Conversely, if detailed exploration reveals that life has not emerged elsewhere despite favorable conditions, it would suggest that this transition represents an extraordinarily improbable event, making Earth's biosphere all the more precious. The story of life's origin and evolution represents more than a local planetary narrative. It exemplifies a fundamental cosmic process whereby matter self-organizes into increasingly complex forms, from subatomic particles to atoms, from atoms to molecules, from molecules to cells, from single cells to complex organisms, and from organisms to societies and civilizations. The universe has generated complexity through natural processes operating over billions of years. Living systems represent a particularly spectacular manifestation of this tendency towards self-organization, achieving levels of structural and functional complexity far beyond those found in non-living systems. This emergence of complex conscious life connects back to the cosmic processes we've traced throughout this journey. The elements essential for life, carbon, nitrogen, oxygen, phosphorus, and others, were forged in the nuclear furnaces of ancient stars and scattered through space by supernovae. The energy that powers nearly all life on Earth comes ultimately from our Sun, a third-generation star formed from recycled stellar material, and the stable planetary environment that allowed life to flourish resulted from the particular formation history of our solar system. In the most literal sense, we are made of stardust, powered by sunlight, and shaped by cosmic processes operating over billions of years. Whether life's emergence represents a cosmic inevitability or an exceptional rarity, the fact of our existence provides a remarkable perspective on the universe. Through conscious observation and scientific inquiry, the cosmos has developed the capacity to comprehend itself. The hydrogen atoms formed in the first few minutes after the Big Bang have been transformed, through stellar nucleosynthesis and biological evolution, into beings capable of reconstructing this cosmic history and contemplating its significance. In this sense, conscious life represents the universe's way of knowing itself, matter that has become aware of its own existence and capable of tracing its origins back to the beginning of time. As we continue our journey through cosmic history, we next examine how life on Earth has been periodically disrupted by catastrophic events from space, asteroid impacts, supernovae, and other cosmic phenomena that have shaped our planet's biological evolution. These events remind us that life exists within a broader cosmic context, subject to influences from beyond our atmosphere, yet they also demonstrate life's remarkable resilience, its ability to recover from devastation and continue its evolutionary journey toward ever greater complexity and consciousness. The story of life's origin on Earth reminds us of our deep connection to cosmic processes. We are not merely inhabitants of the universe, but products of it, complex arrangements of atoms that were forged in stars and assembled through billions of years of chemical and biological evolution. Our consciousness, our curiosity, our capacity for wonder, these most human traits represent the culmination of a cosmic journey that began nearly 14 billion years ago with the Big Bang. Through us, the universe has developed the capacity not just to exist, but to know that it exists, not just to evolve, but to understand its own evolution. Throughout Earth's long history, life has demonstrated remarkable resilience and adaptability, evolving increasingly complex forms and colonizing virtually every environment on the planet. Yet this journey has not been one of smooth, continuous development. Instead, the fossil record reveals that evolution has been punctuated by periodic crises, mass extinction events that wiped out large percentages of existing species in geologically brief intervals. Many of these biological catastrophes had cosmic origins, reminding us that life on Earth exists within a broader universal context, vulnerable to influences from beyond our atmosphere. Mass extinctions represent profound transitions in Earth's biological history, evolutionary bottlenecks through which only a fraction of species survived. Each of these events reshaped the planet's ecosystems, eliminating once dominant groups and creating opportunities for survivors to diversify into vacant ecological niches. Without these periodic reset buttons, the course of evolution would have been dramatically different, and humans might never have evolved. Our very existence is, in a sense, the product of both cosmic catastrophe and biological resilience. The most dramatic and well-studied of these extinction events occurred approximately 66 million years ago, at the boundary between the Cretaceous and Paleogene periods. This event, often called the KPG extinction, formerly known as the KT extinction, eliminated approximately 75% of all species on Earth, including most famously the non-avian dinosaurs that had dominated terrestrial ecosystems for over 150 million years. This single catastrophic episode permanently altered the course of evolution on our planet. The primary cause of the KPG extinction was the impact of an asteroid or comet, approximately 10 to 15 kilometers in diameter, which struck Earth at what is now the Yucatan Peninsula in Mexico. The collision created the Chicxulub crater, a structure approximately 150 kilometers in diameter that still exists today, though largely buried beneath younger sediments. The energy released by this impact was staggering, equivalent to over 1 billion times the energy of the atomic bombs dropped on Hiroshima and Nagasaki. The immediate consequences of this cosmic collision were apocalyptic. The impact would have generated a massive fireball, ejecting molten rock and debris high into the atmosphere and even into space. Much of this material then rained back down across the planet, heating the upper atmosphere and potentially igniting global wildfires. Tsunamis hundreds of meters high would have devastated coastal regions worldwide. Earthquakes far more powerful than any in human experience would have shaken the planet. Perhaps most significantly for global ecosystems, enormous quantities of dust, soot, and sulfur compounds were injected into the atmosphere, blocking sunlight and triggering what scientists call an impact winter. Global temperatures would have plummeted in the months and years following the impact. Photosynthesis would have been severely reduced or halted entirely in many regions, collapsing food webs from the bottom up. The combination of these effects, intense heat, followed by prolonged cooling, acid rain, darkness, collapsed food chains, and habitat destruction, created a global ecological catastrophe. Different groups of organisms were affected to varying degrees by these conditions. Large-bodied land animals, including dinosaurs, were particularly vulnerable due to their high food requirements. Marine ecosystems suffered massive disruptions, especially affecting plankton and coral reefs. In contrast, some groups demonstrated greater resilience. Small-bodied animals, especially those in freshwater environments or underground burrows, survived in greater numbers. Seeds and spores could remain dormant through the worst conditions. These survivors would become the founders of the post-impact world. Among the survivors were small, nocturnal mammals that had existed in the shadow of the dinosaurs for millions of years. With their former competitors eliminated, these mammals rapidly diversified into the ecological niches left vacant by the extinction. This mammalian radiation would eventually produce not only familiar groups like carnivores, hoofed mammals, and primates, but ultimately our own species. In a very real sense, humanity's existence resulted from a cosmic accident. An asteroid that happened to cross Earth's orbit at a particular moment 66 million years ago. The KPG extinction dramatically illustrates the vulnerability of Earth's biosphere to cosmic impacts, but it was neither the first nor the most severe such event. Paleontologists have identified at least 5 major mass extinctions throughout Earth's history, along with numerous smaller extinction events. The most devastating occurred approximately 252 million years ago at the boundary between the Permian and Triassic periods. This great dying eliminated approximately 90% of marine species and 70% of terrestrial vertebrate species. The closest Earth has come to a complete biological reset since complex life evolved. The causes of the Permian-Triassic extinction appear more complex than those of the KPG event. The primary driver was likely massive volcanic eruptions in what is now Siberia, which released enormous quantities of carbon dioxide and other gases, triggering severe global warming ocean acidification and widespread oxygen depletion in the oceans. However, some evidence suggests that cosmic influences may have played a role as well. Impact structures dating to this period have been identified, and some researchers have proposed that the Siberian eruptions themselves might have been triggered by a large asteroid impact on the opposite side of the planet. Between these two most severe events, another major extinction occurred at the boundary between the Triassic and Jurassic periods, approximately 201 million years ago. This event eliminated many competitors of the dinosaurs, allowing this group to become dominant in terrestrial ecosystems throughout the subsequent Jurassic and Cretaceous periods. Again, while massive volcanic eruptions associated with the breakup of the supercontinent Pangaea appear to have been the primary cause, researchers have not ruled out a contributing role from cosmic impacts. Earlier in Earth's history, two other major extinction events reshaped the biosphere. The late Devonian extinction, occurring in pulses between approximately 375 and 360 million years ago, severely affected marine ecosystems, eliminating many coral species and primitive fish. The Ordovician-Silurian extinction, approximately 445 million years ago, coincided with a severe ice age and may have been triggered by a gamma-ray burst, an intense flash of radiation from a distant exploding star that could have damaged Earth's protective ozone layer. Beyond these Big Five mass extinctions, numerous smaller extinction events have occurred throughout Earth's history, many potentially linked to cosmic phenomena. Evidence for multiple impact events exists in the geological record, including craters of various sizes and ages scattered across the planet's surface, layers rich in iridium, an element rare in Earth's crust, but more common in asteroids, and shocked quartz, which forms under the extreme pressures of an impact, provide additional evidence for these cosmic collisions. The threat of asteroid and comet impacts continues today. Earth orbits the Sun within a cosmic shooting gallery of objects, ranging from dust-sized particles to bodies many kilometers in diameter. Small meteoroids enter Earth's atmosphere daily, most burning up as meteors, shooting stars in the night sky. Larger objects capable of reaching the ground as meteorites strike less frequently. The Tunguska event of 1908, which flattened approximately 2,000 square kilometers of Siberian forest, resulted from the atmospheric explosion of an object probably 50 to 60 meters in diameter. The Chelyabinsk meteor of 2013, which injured more than 1,500 people, was caused by an object approximately 20 meters across. Truly catastrophic impacts, like the one that triggered the KPG extinction, occur on timescales of many millions of years. Nevertheless, numerous near-Earth objects, NEOs, have been identified with orbits that cross Earth's path around the Sun. Space agencies around the world now maintain programs to detect and track these objects, calculating their orbits to determine whether any pose a collision risk. For the first time in Earth's history, a species has developed the capacity to potentially predict and prevent a cosmic catastrophe before it occurs. Asteroids and comets represent only one category of cosmic threats to Earth's biosphere. An even more energetic phenomenon, gamma-ray bursts, GRBs, could potentially trigger extinctions from thousands of light-years away. These extraordinarily powerful explosions, among the most energetic events in the universe, release intense beams of radiation that could strip away Earth's protective ozone layer if our planet happened to lie in their path. Some scientists have suggested that the Ordovician-Silurian extinction might have been triggered by such an event. Supernovae, the explosive deaths of massive stars, represent another potential cosmic hazard. A supernova occurring within approximately 50 to 100 light-years of Earth could flood our planet with harmful radiation, potentially damaging the ozone layer and exposing the biosphere to increased ultraviolet radiation. Beyond these direct effects, the charged particles ejected by such an explosion could compress Earth's magnetic field, potentially exposing the planet to dangerous cosmic rays. Some researchers have suggested that nearby supernovae might have influenced Earth's climate and biology at various points in our planet's history. Our Sun itself, usually a stable provider of the energy that powers Earth's biosphere, occasionally produces violent outbursts with potentially serious consequences. Solar flares and coronal mass ejections can release enormous bursts of energy and charged particles that interact with Earth's magnetic field and atmosphere. While our planet's magnetic field generally protects us from the worst effects of these solar storms, particularly intense events could potentially disrupt power grids, disable satellites, and expose astronauts or high-altitude aircraft to dangerous radiation levels. In the longer term, the Sun's natural evolution poses an existential challenge to life on Earth. As our star ages, it gradually becomes brighter, a process that will continue over the next 5 billion years until the Sun enters its red giant phase. Long before then, increasing solar luminosity will disrupt Earth's climate system, eventually rendering our planet uninhabitable. The awareness of this cosmic timeline highlights the ultimately temporary nature of Earth as a habitable world, despite the billions of years of habitability that remain. While these cosmic threats might seem alarming, the geological record provides an important perspective. Major extinction-level cosmic impacts appear to occur on timescales of many millions of years, far longer than the existence of human civilization or even our species. More frequent, smaller impacts, while potentially devastating on local or regional scales, do not threaten the continuity of the biosphere as a whole. The night sky, for all its wonder, is not filled with imminent dangers to our existence. Moreover, the same fossil record that reveals past catastrophes also demonstrates life's remarkable resilience. After each mass extinction, surviving lineages diversified to fill available ecological niches, often achieving even greater diversity than existed before the crisis. Life as a phenomenon has persisted on Earth for at least 3.5 billion years, despite numerous challenges from both cosmic and terrestrial sources. This resilience offers a profound perspective on the relationship between life and the cosmos. Indeed, cosmic catastrophes have played a constructive role in biological evolution. The periodic reshuffling of ecological relationships following extinction events created opportunities for evolutionary innovation that might not have occurred in more stable conditions. Without the asteroid impact that eliminated the dinosaurs, mammals might never have diversified into the numerous forms we see today, including humans. Our existence is thus not merely despite cosmic catastrophes, but because of them. A striking example of how disorder can ultimately generate new forms of order. The KPG extinction particularly illustrates this principle. The impact eliminated approximately 75% of species, causing immense ecological disruption, yet it also broke the dominance of large reptiles that had persisted for over 150 million years, creating space for mammals to diversify. Small-bodied animals with adaptations that happen to be suitable for surviving the impact. Nocturnal lifestyles, the ability to eat varied diets, endothermy, warm-bloodedness, suddenly had evolutionary advantages. These survivors became the ancestors of most modern mammal groups, including primates and eventually humans. This pattern of destruction followed by diversification appears repeatedly in evolutionary history. After the Permian-Triassic extinction eliminated approximately 90% of marine species, the surviving 10% gave rise to new marine ecosystems that included the ancestors of many modern groups. The Ordovician-Silurian extinction was followed by the diversification of jawed fishes, which would eventually give rise to all vertebrates with jaws, including humans. Each crisis served as an evolutionary bottleneck, filtering existing diversity and establishing new starting points for subsequent evolution. As we peer deeper into cosmic history, we approach a boundary that challenges not just our understanding of physics, but the very nature of understanding itself. What existed before the Big Bang? This seemingly simple question leads us to the frontier of human knowledge, a realm where science, philosophy, and even logic itself begin to blur. The question itself contains a profound assumption that there was a before, but time as we know it may have begun with the Big Bang. Asking what came before the beginning of time might be like asking what's north of the North Pole. a question that appears meaningful but contains a fundamental misconception. As the renowned physicist Stephen Hawking once observed, asking what came before the Big Bang might be like asking what's south of the South Pole. There is no south beyond the southernmost point, just as there may be no before prior to the first moment. Yet this philosophical barrier hasn't stopped scientists from developing theories about pre-Big Bang conditions. These models attempt to extend our understanding beyond the apparent beginning, suggesting ways in which our universe might connect to a larger reality. While we cannot observe anything before the Big Bang directly, the earliest light we can detect comes from hundreds of thousands of years afterward. Mathematics allows us to explore possible scenarios that might have led to our universe's birth. One compelling class of theories proposes that our universe exists within a much larger multiverse, an endless sea of bubble universes, each with its own Big Bang moment. In this eternal inflation model, space itself expands exponentially in most regions, but occasionally small patches stop inflating and become separate universes with their own physical laws and histories. Our entire observable cosmos might be just one bubble that formed when a tiny region of this expanding metaverse decelerated and allowed matter and energy to condense. This scenario suggests that before the Big Bang, our region of space was part of this rapidly expanding metaverse. Our universe didn't emerge from nothing, but rather budded off from a pre-existing state that continues to generate new universes endlessly. If true, creation never had an absolute beginning. Our particular cosmic story had a starting point, but the larger reality from which it emerged might be eternal. Another approach comes from loop quantum cosmology, which applies the principles of quantum mechanics to space-time itself. In this framework, as we trace cosmic history backward toward the Big Bang, the universe doesn't reach an infinitely dense singularity, as Einstein's general relativity suggests. Instead, when compressed to a certain threshold, quantum effects cause space-time to bounce, transitioning from contraction to expansion. This suggests our universe emerged from a previous contracting phase, perhaps another universe that collapsed before ours expanded. This bouncing universe model proposes a cyclical cosmos, potentially extending infinitely into the past and future. Rather than a singular creation event, the Big Bang would represent a transitional moment, the latest in an endless series of bounces between contracting and expanding phases. The apparent beginning of our universe resulted from the collision of higher dimensional membranes, vast cosmic structures existing in this more complex geometry. In this brane cosmology, before the Big Bang, there were these higher dimensional structures interacting according to physics we're still trying to understand. Our universe's beginning might have been triggered by the violent collision of such branes, releasing enormous energy that manifested as our Big Bang. If true, our universe would be just one event in a more complex, higher dimensional reality that operates according to rules we're only beginning to glimpse. Quantum mechanics itself suggests another intriguing possibility. The uncertainty principle, a cornerstone of quantum physics, establishes that empty space is never truly empty. Even perfect vacuum fluctuates with particles and antiparticles briefly popping into existence before annihilating each other and disappearing. These quantum fluctuations represent a fundamental restlessness in the fabric of reality itself. Understanding these past catastrophes and their influence on evolution provides valuable context for humanity's current relationship with our planet and the broader cosmos. For the first time in Earth's history, a single species, Homo sapiens, has developed the technological capacity to detect and potentially prevent certain cosmic threats. Asteroid detection and tracking programs represent the first steps toward a planetary defense capability that was never before possible. Our awareness of these hazards, combined with our growing technological prowess, offers the possibility of breaking the cycle of periodic extinction events that has characterized Earth's history. At the same time, we have also become a geological and ecological force ourselves, capable of triggering biosphere changes comparable to those caused by cosmic catastrophes. The current human-induced loss of biodiversity often called the sixth mass extinction, is occurring at rates similar to or exceeding those of previous extinction events, though through different mechanisms: habitat destruction, pollution, overexploitation, and climate change, rather than asteroids or volcanic eruptions. This sobering reality highlights the profound responsibility that comes with our unprecedented influence over planetary systems. Our study of cosmic catastrophes also informs our search for life beyond Earth. If mass extinctions represent a common feature of biological evolution on habitable worlds, then the development of complex intelligent life might require not only suitable planetary conditions, but also the right pattern of periodic disruptions, neither too frequent to prevent complexity from evolving, nor too rare to drive evolutionary innovation. This perspective adds nuance to our understanding of habitability and the potential distribution of complex life throughout the universe. The relationship between Earth's biosphere and the cosmos extends beyond catastrophes. Life on our planet depends fundamentally on cosmic energy sources, primarily sunlight, but also the geothermal heat, partly generated by radioactive elements forged in ancient supernovae. The elements essential for biology: carbon, nitrogen, oxygen, phosphorus, and others, were created in stellar processes and delivered to the forming Earth. Even the water that makes our planet habitable may have been partly delivered by comets, the same class of objects that compose impact threats. Our existence thus reflects both the creative and destructive aspects of cosmic processes. This duality, creation and destruction, order and chaos, appears to be a fundamental feature of cosmic evolution. The same gravitational processes that form stars and planets also produce the orbital dynamics that occasionally send asteroids on collision courses with Earth. The supernovae that threaten nearby planetary systems with radiation also create and distribute the heavy elements necessary for rocky planets and complex chemistry. The universe builds with one hand and tears down with the other, yet the long arc of cosmic history tends toward increasing complexity. As we continue our journey through cosmic history, we move from these dramatic encounters between life and the cosmos to another profound mystery: the accelerating expansion of the universe driven by dark energy. This phenomenon, operating on the largest cosmic scales, will ultimately determine the fate of all structures in the universe, from superclusters of galaxies down to the atoms that compose them. The story of cosmic expansion connects the earliest moments after the Big Bang to the far future, completing our narrative arc from the universe's birth toward its possible endings. The mass extinctions that have periodically reshaped life on Earth remind us of our planet's place within a broader cosmic context. We orbit our star within a dynamic solar system, itself situated within a spiral arm of the Milky Way galaxy, which moves through intergalactic space within the local group and Laniakea supercluster. Throughout this cosmic neighborhood, energetic processes unfold. Stars explode, black holes merge, asteroids collide, occasionally intersecting with Earth's journey through space with profound consequences for life. Yet perhaps the most remarkable consequence of this long sequence of cosmic events and biological evolution is the emergence of minds capable of reconstructing this very history. Through science, we have developed the capacity to read the record preserved in rocks and ice, to detect the faint afterglow of the Big Bang, to understand the nuclear processes powering stars, and to trace the evolutionary pathways from single-celled organisms to the complex biosphere we inhabit. We have become the universe's way of knowing itself, conscious entities assembled from atoms forged in stars, living on a planet shaped by both cosmic creativity and catastrophe. In the early decades of the 20th century, astronomers made an astounding discovery that would forever change our understanding of the cosmos. The universe, rather than being static and eternal as previously assumed, is actually expanding. All galaxies beyond our local group are moving away from us, and the farther they are, the faster they recede. This observation, first made by Edwin Hubble in 1929, initiated a profound reconceptualization of cosmic history and destiny, but the story would take an even more surprising turn toward the end of the century, when astronomers discovered that this expansion isn't slowing down as expected, but actually accelerating, driven by a mysterious force we now call dark energy. The realization that the universe is expanding emerged from careful observations of distant galaxies. Using the 100-inch Hooker telescope at Mount Wilson Observatory in California, Edwin Hubble measured the distances to numerous galaxies by identifying individual stars within them called Cepheid variables. These stars pulsate with a regular rhythm that correlates with their intrinsic brightness, making them reliable cosmic yardsticks for measuring distances. Meanwhile, astronomer Vesto Slipher had been measuring the spectra of light from various galaxies. He found that specific patterns of absorption lines, dark bands in the spectrum where certain wavelengths are absorbed by elements in the galaxy, were shifted toward the red end of the spectrum compared to what would be observed in a laboratory on Earth. This redshift, as it became known, indicated that these galaxies were moving away from our own. When Hubble combined his distance measurements with Slipher's velocity data, a remarkable pattern emerged. There was a direct relationship between a galaxy's distance and its recession velocity. The farther a galaxy was from Earth, the faster it appeared to be moving away. This correlation, now known as Hubble's law, led to an extraordinary conclusion. The entire universe is expanding, with space itself stretching between galaxies. This discovery aligned perfectly with Albert Einstein's general theory of relativity, which had been developed a decade earlier. Einstein's equations naturally predicted an expanding or contracting universe, not a static one. Initially, Einstein had added a term to his equations, the cosmological constant, specifically to counteract this prediction and maintain a static universe, which was the prevailing view at the time. Upon learning of Hubble's discovery, Einstein reportedly called the cosmological constant his greatest blunder. Ironically, this mathematical term would later find new relevance in explaining the accelerating expansion of the universe. The expansion of the universe has profound implications for our understanding of cosmic history. If all galaxies are moving away from each other, then in the past, they must have been closer together. Tracing this expansion backward in time leads inevitably to the conclusion that approximately 13.8 billion years ago, all matter and energy in the observable universe was compressed into an incredibly hot, dense state, the moment we call the Big Bang. The expanding universe thus provides one of the key pieces of evidence for the Big Bang theory, fundamentally reshaping our understanding of cosmic origins. For decades after Hubble's discovery, cosmologists assumed that the expansion of the universe would gradually slow down over time due to gravity. The mutual gravitational attraction between all matter in the universe should act as a cosmic brake, gradually decelerating the expansion. The key question seemed to be whether there was enough matter to eventually halt and reverse the expansion, leading to a big crunch, or whether the universe would expand forever, but at an ever-diminishing rate. In the 1998, two independent teams of astronomers set out to measure this deceleration by observing extremely distant supernovae, specifically type Ia supernovae, which result from the explosive death of white dwarf stars. These cosmic explosions have a crucial property that makes them valuable for cosmological measurements. They all reach approximately the same peak brightness. By measuring how much dimmer these distant supernovae appeared compared to what would be expected based on their redshift, astronomers could determine how the expansion rate of the universe has changed over time. The results, announced almost simultaneously by the Supernova Cosmology Project, led by Saul Perlmutter and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, shocked the scientific community. Instead of finding the expected deceleration, both teams discovered that the expansion of the universe is accelerating. Galaxies are moving away from each other at an ever-increasing rate. This finding, which earned Perlmutter, Schmidt, and Rees the 2011 Nobel Prize in Physics, required a dramatic rethinking of our understanding of the universe. What could be driving this cosmic acceleration? Whatever it is, must exert a repulsive force that counteracts gravity on the largest scales. Astronomers and physicists call this mysterious driving force dark energy, but the name serves more as a placeholder for our ignorance than an explanation. We know what dark energy does. It accelerates the expansion of the universe, but its fundamental nature remains one of the greatest unsolved mysteries in modern physics. One possibility is that dark energy represents the energy inherent in empty space itself, what physicists call vacuum energy or zero-point energy. According to quantum field theory, even perfect vacuum isn't truly empty, but seethes with virtual particles and fields that continuously pop in and out of existence. This vacuum energy could manifest as a kind of negative pressure that drives space to expand faster. This explanation effectively resurrects Einstein's cosmological constant, but with a new interpretation. Rather than an arbitrary mathematical term added to maintain a static universe, it would represent a fundamental property of space itself, an energy density that remains constant as the universe expands, causing the expansion to accelerate. Current measurements suggest that if dark energy is indeed constant, it accounts for approximately 68% of the total energy content of the universe. Another possibility is that dark energy isn't constant, but changes over time. Various theoretical models, often grouped under the term quintessence, propose a dynamic dark energy field that pervades the universe and evolves throughout cosmic history. These models predict that the strength of dark energy could increase or decrease over time, potentially leading to different cosmic futures than those expected from a constant dark energy. A third, more radical possibility is that dark energy isn't a new component of the universe at all, but rather indicates a breakdown in our understanding of gravity on the largest scales. Perhaps Einstein's general relativity, while extraordinarily successful at describing gravity in the solar system and other tested environments, requires modification at cosmic scales. Various modified gravity theories have been proposed that might explain the accelerating expansion without invoking dark energy as a separate component. Determining the nature of dark energy has become one of the central quests of modern cosmology. Several major observational projects are underway or planned, including the Dark Energy Survey, the Euclid mission, and the Nancy Grace Roman Space Telescope, all designed to measure the expansion history of the universe with unprecedented precision. By tracking exactly how the expansion rate has changed over cosmic time, these projects aim to distinguish between competing dark energy models. The discovery of the accelerating universe has profound implications for cosmic destiny. If dark energy maintains its current strength or increases over time, the expansion will continue to accelerate forever. In this scenario, galaxies beyond our local group will recede faster and faster, eventually disappearing from view as their light becomes too redshifted to detect. In the extremely distant future, trillions of years from now, even nearby galaxies like Andromeda that are currently bound to the Milky Way by gravity would be torn away, leaving our galaxy increasingly isolated in an expanding void. This big freeze scenario presents a rather bleak ultimate fate for the cosmos. Stars would eventually exhaust their fuel and burn out. Black holes would gradually evaporate through Hawking radiation. Matter itself might ultimately decay. The universe would become an increasingly cold, dark, and diffuse place, with former structures separated by ever greater expanses of empty space. An even more extreme possibility, called the Big Rip, could occur if dark energy increases in strength over time. In this scenario, the accelerating expansion eventually becomes so powerful that it overcomes not just the gravitational bonds between galaxies, but also those holding individual galaxies, solar systems, planets, and ultimately atoms themselves together. The universe would literally tear itself apart, with all structures disintegrating as space expands too rapidly for any force to maintain cohesion. Conversely, if dark energy weakens over time, gravity could eventually reassert dominance, potentially leading to a big crunch, where the expansion reverses and the universe recollapses. Or a more complex scenario might unfold, with multiple phases of acceleration and deceleration. The ultimate fate of the cosmos thus hinges on the nature of dark energy, a component we currently understand largely through its effects rather than its fundamental character. The mystery of dark energy highlights the limits of our current understanding of physics. It operates at the intersection of cosmology, which deals with the universe at its largest scales, and quantum physics, which describes reality at its smallest scales. Reconciling these domains has proven extraordinarily challenging. Our best theory of gravity, general relativity, doesn't easily integrate with quantum mechanics, creating significant hurdles for fully explaining phenomena like dark energy. When cosmologists calculate the expected vacuum energy from quantum field theory and compare it to the observed value of dark energy, they find a discrepancy of approximately 120 orders of magnitude, often described as the worst prediction in physics. This cosmological constant problem suggests that either our understanding of vacuum energy is profoundly incomplete, or dark energy arises from something entirely different. Adding to the complexity is another mysterious component of the universe: dark matter. Unlike dark energy, which appears to be evenly distributed throughout space and acts as a repulsive force, dark matter clumps together under gravity and exerts only gravitational attraction. It doesn't emit, absorb, or reflect light, making it invisible to direct observation, but its gravitational effects on visible matter reveal its presence. Together, dark energy and dark matter account for approximately 95% of the total energy content of the universe, with ordinary visible matter, stars, planets, gas, dust, and all living things making up only about 5%. This startling realization emerged gradually over the latter half of the 20th century, fundamentally changing our cosmic perspective. Our universe is dominated by components we cannot directly see and currently don't fully understand. The expansion of the universe, first discovered by Hubble and later found to be accelerating, has revealed itself as a central, defining feature of our cosmos. It shapes not only our understanding of the past, leading back to the Big Bang, but also our expectations for the future. The nature of this expansion and the dark energy driving its acceleration represent some of the most profound mysteries in modern science. Sitting at the frontier of physics and cosmology, this cosmic expansion also provides the backdrop for all the processes we've traced throughout this journey. While stars form, galaxies evolve, and life emerges on at least one planet, the universe as a whole continues its inexorable expansion. Structures form and evolve within this expanding framework, their development influenced by both the expansion itself and their own internal dynamics. On the largest scales, the expansion of the universe competes with gravity's attractive force to shape the cosmic web, that network of galaxy clusters and filaments that forms the universe's basic large-scale structure. Where gravity dominated in the early universe, matter could collapse to form bound structures like galaxies and clusters. Where the expansion dominated, voids formed, vast regions with relatively little matter. As dark energy has grown more dominant over time, the formation of larger structures has gradually ceased, freezing the cosmic web into its current configuration. The current balance between expansion and gravitational attraction creates the conditions that allow complex structures to exist. Had the universe expanded too quickly in its early phases, gravity could never have pulled matter together to form galaxies, stars, and planets. Had it expanded too slowly, all matter might have recollapsed before stars could complete their life cycles and produce the heavy elements necessary for planets and life. The just right expansion rate we observe, sometimes called a cosmic coincidence, has allowed the universe to develop the rich complexity we observe today. This apparent fine-tuning has led some scientists to propose the existence of a multiverse, a vast or infinite collection of universes with different physical laws and expansion rates. In this scenario, we naturally find ourselves in a universe compatible with our existence, as observers could only evolve in universes with suitable conditions. This anthropic reasoning suggests that our universe's properties, including its expansion rate and the strength of dark energy, might be understood not as unique inevitabilities, but as one combination among many possible universal configurations, selected by the requirement that observers like us must be able to evolve. Whether our universe is unique or one of many, its expansion represents a fundamental process that has shaped cosmic evolution from the earliest moments to the present day and will continue to influence its development far into the future. The discovery of this expansion ranks among humanity's most profound scientific insights, completely transforming our understanding of cosmic origins, evolution, and destiny. As we continue to study this expansion and the mysterious dark energy driving its acceleration, we push the boundaries of fundamental physics. The quest to understand dark energy may ultimately require a deeper synthesis of quantum mechanics and general relativity, perhaps leading to a comprehensive theory of quantum gravity that would represent one of the greatest achievements in the history of physics. This ongoing investigation exemplifies science at its most ambitious, grappling with the fundamental nature of space, time, energy, and the universe itself. From Hubble's initial observations to the discovery of accelerating expansion and the current quest to characterize dark energy, cosmologists have gradually pieced together an increasingly sophisticated understanding of our expanding universe. Yet, significant mysteries remain, beckoning future generations of scientists to continue this cosmic inquiry. The story of the universe's expansion connects directly to the Big Bang with which we began our journey. The same expansion that Hubble observed in nearby galaxies, when traced backward in time, leads to the hot, dense state from which our universe emerged. And when projected forward, this expansion, now accelerating due to dark energy, shapes possible futures for our cosmos. The expansion of the universe thus serves as a thread connecting cosmic past, present, and future, a fundamental process underlying the entire cosmic narrative. As we look out at distant galaxies, measuring their redshifts and calculating their recession velocities, we observe not just their motion, but the dynamic nature of space itself. The universe is not a static stage upon which cosmic evolution unfolds, but an active, expanding entity whose very fabric stretches over time. This expanding framework has profoundly influenced every aspect of cosmic history, from the formation of the first atoms to the evolution of galaxies, from the birth of stars to the emergence of life. In the next section, we'll explore how this expansion shapes possible futures for our universe, examining various scenarios for cosmic destiny based on different models of dark energy and its long-term behavior. The same cosmic processes we've traced from the Big Bang through galaxy formation, stellar evolution, and the emergence of life will continue far into the future, playing out against the backdrop of an ever-expanding cosmos whose ultimate fate remains one of the greatest mysteries in science. As we've journeyed from the Big Bang through the formation of galaxies, stars, and planets to the emergence of life and consciousness, we've traced a cosmic history spanning approximately 13.8 billion years. But what of the future? What ultimate fate awaits our universe in the distant reaches of time? The discoveries of cosmic expansion and its acceleration have profoundly shaped our understanding of possible cosmic futures, suggesting several distinct scenarios for how the universe might evolve over the coming billions, trillions, and perhaps even greater spans of time. The long-term destiny of our universe hinges primarily on the nature of dark energy, that mysterious force driving the accelerating expansion. Depending on whether dark energy remains constant, strengthens, weakens, or exhibits more complex behavior over time, the cosmos could face several possible futures, ranging from endless expansion to eventual collapse, or even more exotic possibilities. Let us explore these potential cosmic destinies, tracing the fate of galaxies, stars, planets, and matter itself as the universe continues its evolutionary journey. The scenario currently best supported by observational evidence is known as the Big Freeze, or heat death. In this vision of cosmic destiny, dark energy maintains its current strength, causing the universe's expansion to accelerate indefinitely. Galaxies beyond our local group would recede ever faster, eventually moving away more rapidly than their light could travel toward us. One by one, distant galaxies would appear to wink out as their light becomes too redshifted to detect, leaving our observable universe increasingly empty. Within this expanding cosmos, stars would continue their life cycles for many billions of years to come. Our own Sun has only completed about half its 10 billion year lifespan as a main sequence star. In about 5 billion years, it will exhaust the hydrogen in its core, expand into a red giant, and eventually shed its outer layers to form a planetary nebula with a white dwarf star at its center. This white dwarf, the dense, cooling core of our once brilliant Sun, will slowly radiate away its heat over hundreds of billions of years, eventually becoming a cold, dark remnant. Throughout the broader universe, similar processes would unfold. Blue, massive stars would burn through their fuel quickly, exploding as supernovae and leaving behind neutron stars or black holes. Smaller, redder stars would persist much longer, some continuing to shine dimly for trillions of years. But eventually, star formation itself would cease as the raw material, primarily hydrogen gas, becomes exhausted. The universe would enter what astronomers call the degenerate era, a period dominated by brown dwarfs, white dwarfs, neutron stars, and black holes, the cold or compact remnants of once brilliant stars. Over unfathomably long timescales, even these remnants would continue to evolve. White dwarfs and neutron stars would gradually cool, fading to black. Brown dwarfs, failed stars too small to sustain hydrogen fusion, would similarly cool to equilibrium with the ever colder background temperature of expanding space. The universe would grow increasingly dark, with only occasional flashes of light from rare events like colliding neutron stars or matter falling into black holes. Black holes themselves, once thought to be eternal, would eventually begin to decay through a quantum process called Hawking radiation, whereby they slowly emit particles and lose mass. This process occurs incredibly slowly for large black holes. The supermassive black hole at the center of our galaxy would take approximately 100 quintillion, 1 followed by 20 zeros, years to evaporate completely. But given enough time, even these mighty objects would dissipate, converting their enormous mass into radiation that would itself be stretched to insignificance by cosmic expansion. In the most extreme extrapolations of this scenario, after black holes have evaporated and all other structures have decayed, the universe would consist primarily of extremely low-energy photons, neutrinos, electrons, and positrons, all separated by ever-increasing distances as space continues to expand. Matter as we know it would essentially cease to exist, with even protons and neutrons having decayed over these vast timescales. The universe would reach a state of maximum entropy, a cold, diffuse soup of elementary particles, unable to perform any useful work or organize into complex structures. This state of affairs, the final stage of the Big Freeze, represents a kind of equilibrium from which no further large-scale changes would occur. This vision of cosmic history, from the hot, dense Big Bang to a cold, empty void, presents a complete life cycle for the universe. Like individual stars that burn brilliantly for a time before fading, the cosmos itself might experience a finite period of creative activity, producing galaxies, stars, planets, and perhaps life, before gradually sliding toward eternal darkness. The universe would not end with a dramatic event, but would instead slowly fade away, its once vibrant structures dissolving into an ever-expanding emptiness. However, this Big Freeze scenario assumes that dark energy maintains its current properties indefinitely. If dark energy instead grows stronger over time, a more dramatic fate might await the cosmos. In what cosmologists call the Big Rip scenario, the accelerating expansion would eventually become so powerful that it overcomes all other forces holding matter together. Galaxies would be torn apart as the space between their stars expands too rapidly for gravity to maintain cohesion. Solar systems would disintegrate as planets are ripped from their orbits. Even atoms themselves would eventually be torn asunder as the space between subatomic particles expands faster than electromagnetic forces can hold them together. The timeline for such a scenario depends on how quickly dark energy strengthens, but some models suggest it could occur within the next 100 billion years, a long time by human standards but relatively brief in cosmic terms. The universe would effectively destroy itself through its own expansion, with all structures from the largest to the smallest disintegrating in a final cosmic cataclysm. Conversely, if dark energy weakens over time, gravity might eventually reassert dominance, halting and potentially reversing the cosmic expansion. This big crunch scenario would see the universe stop expanding and begin to contract, with galaxies moving closer together rather than farther apart. Eventually, all matter would be compressed into an incredibly hot, dense state, similar to the Big Bang. Some theorists have speculated that this compression could potentially seed another expansion, a new Big Bang giving birth to a new universe, perhaps with different physical laws and constants. This possibility connects to a broader cyclical model, sometimes called the Big Bounce, in which the universe oscillates between periods of expansion and contraction. Each cycle would end with a big crunch and begin with a big bang, potentially continuing indefinitely. While such models face significant theoretical challenges, particularly regarding how physical information might transfer from one cycle to the next, they offer an alternative to both the eternal expansion of the Big Freeze and the finality of the Big Crunch. Yet another possibility emerges from quantum field theory, a scenario called vacuum decay. Our current universe may exist in what physicists call a false vacuum state, a seemingly stable configuration that is actually vulnerable to quantum tunneling into a lower energy state. If a bubble of true vacuum were to form somewhere in the cosmos, it would expand at nearly the speed of light, transforming the very fabric of reality as it grows. The laws of physics themselves would change within this expanding bubble, likely making complex structures like atoms, stars, and life impossible. This transition would essentially erase the universe as we know it, replacing it with a new reality governed by different physical principles. The likelihood of such vacuum decay remains highly speculative and depends on the detailed structure of quantum fields that we have yet to fully understand. However, if our universe does exist in a false vacuum state, this decay becomes inevitable given enough time, providing yet another possible mechanism for cosmic transformation. Beyond these relatively well-developed scenarios lie more speculative possibilities. Could dark energy exhibit oscillatory behavior, causing the universe to cycle between periods of accelerating and decelerating expansion? Might quantum effects near the end of a big crunch spawn multiple new universes rather than just one, creating a branching tree of cosmic offspring? Could intelligent life eventually develop the capacity to influence cosmic evolution, perhaps even creating baby universes with carefully selected properties? These questions push the boundaries of current physics, but highlight the rich landscape of possibilities for cosmic futures. Whatever the ultimate fate of the universe might be, we can predict with some confidence the major milestones of cosmic evolution over the next few billion years. Our Milky Way galaxy will collide and merge with the neighboring Andromeda galaxy in approximately 4.5 billion years, creating a larger elliptical galaxy, sometimes called Milkomeda. Around the same time, our Sun will enter its red giant phase, engulfing the inner planets including Mercury and Venus, and possibly Earth as well. Even if our planet survives, its oceans will evaporate and its surface will be sterilized by the Sun's increased luminosity. Over the next few tens of billions of years, star formation will continue throughout the universe, though at a decreasing rate as the available gas is gradually locked up in stars or ejected from galaxies. The cosmic web of galaxy clusters and filaments will become increasingly frozen in its current configuration as the accelerating expansion prevents new, large-scale structures from forming. By 100 billion years from now, all galaxies beyond our local group will have receded beyond the cosmic horizon, becoming unobservable to any astronomers who might still exist in our region. Within our merged local collection of galaxies, star formation will eventually cease entirely once the available gas is exhausted, perhaps within a few trillion years. The remaining stars will slowly burn through their fuel and die, leaving behind a collection of stellar remnants, white dwarfs, neutron stars, and black holes orbiting in the darkness. Occasionally, these remnants will collide, producing brief flashes of light in an otherwise dark galaxy. On even longer timescales, the stellar remnants themselves will begin to decay. White dwarfs and neutron stars will cool to the background temperature of space. Black holes will gradually evaporate through Hawking radiation, with smaller ones disappearing first and the supermassive black holes lasting the longest. The matter that once composed brilliant stars, beautiful spiral galaxies, and perhaps even living worlds will be converted first to cold remnants and eventually to radiation that itself grows ever more diffuse as space continues to expand. This vision of the far future might seem bleak from a human perspective, a universe growing ever colder, darker, and emptier. Yet even this scenario contains its own kind of majesty. The same physical laws that allowed for the emergence of structure, complexity, and eventually life also dictate this long, slow decline. The cosmos follows its own rhythm, vastly slower than human timescales, playing out processes over trillions and quadrillions of years that mirror in some ways the life cycles we observe in the biological world. Moreover, this projection of cosmic future assumes that intelligent life remains a passive observer of these processes, rather than an active participant. Perhaps the most intriguing possibility is that consciousness itself might influence cosmic evolution. While speculative, some physicists and philosophers have suggested that sufficiently advanced civilizations might develop technologies to create new universes, modify the properties of space-time, or transfer information and complexity beyond the death of our current cosmos. In a universe where matter has organized itself into beings capable of understanding that universe, might those beings eventually develop the capacity to shape cosmic destiny? This question connects to broader philosophical considerations about purpose and meaning in an evolving universe. Is consciousness simply a temporary phenomenon in cosmic history, a brief flicker of awareness in a universe destined for darkness? Or might consciousness represent something more fundamental, perhaps even an essential driver of cosmic evolution? While science cannot currently answer such questions definitively, they emerge naturally from our exploration of cosmic futures. What we can say with confidence is that the universe has exhibited a remarkable tendency toward increasing complexity throughout its history. From the simplicity of the post-Big Bang cosmos, with its nearly uniform distribution of hydrogen and helium, emerged the rich cosmic ecosystem we observe today. Galaxies, stars, planets, and on at least one world, the extraordinary complexity of living systems and conscious minds. This journey from simplicity to complexity, from homogeneity to diversity, represents one of the most fundamental patterns in cosmic evolution. Will this trend toward increasing complexity continue indefinitely, perhaps through forms of organization we cannot currently imagine? Or will entropy ultimately prevail, with the universe's creative era representing just a temporary deviation from the inexorable trend toward disorder? The answers depend in part on the nature of dark energy and the resulting cosmic expansion, but also potentially on the future evolution of intelligent life and technology. For now, we find ourselves in what might be called the stelliferous era, the approximately 10 trillion year period when stars shine abundantly, providing energy for complex processes including life. We exist during a remarkably fecund period in cosmic history, when galaxies are still forming stars, planets are coalescing around those stars, and at least one species has developed the capacity to comprehend these processes. Whether by chance or necessity, conscious observers have emerged during an era when the universe offers both the energy resources and the physical stability necessary for complex life. This coincidence that we exist during what appears to be a relatively brief window of cosmic habitability raises profound questions about the relationship between consciousness and cosmos. Are we merely fortunate beneficiaries of the current cosmic era, destined to vanish as the universe continues its evolution toward darkness? Or does consciousness itself represent an emergent property of complex systems that might find ways to perpetuate itself through the changing cosmic landscape? While such questions stretch beyond the reach of current science, they arise naturally from our exploration of cosmic futures. By projecting the evolution of the universe forward in time, based on our best understanding of physics and cosmology, we encounter not just scientific questions about the behavior of matter and energy, but philosophical ones about purpose, meaning, and the role of mind in the cosmos. As we contemplate these possible futures, we should remember that our understanding remains provisional. Just as Edwin Hubble's discovery of cosmic expansion in the 1920s smashed the prevailing view of a static universe, and the 1998 discovery of accelerating expansion overturned expectations of gradual deceleration, future observations and theoretical advances may reveal aspects of cosmic evolution currently unimagined. The universe has surprised us before, and likely will again. This humility about our knowledge reminds us that the story of the universe is not just a tale of the past, but an ongoing narrative. We stand at a particular moment in cosmic history, able to look backward with increasing scientific clarity, but able to project forward only with increasing uncertainty. The future remains unwritten, shaped by the same fundamental laws we've studied, but playing out in ways we can model only imperfectly. Whatever ultimate fate awaits our universe, whether endless expansion, eventual recollapse, catastrophic instability, or something not yet conceived, the cosmos will continue its evolutionary journey long after human observers have vanished. Stars will continue their life cycles, galaxies will interact and evolve, and physical processes will unfold according to the same laws that have governed cosmic evolution since the Big Bang. Yet, through science, art, philosophy, and other forms of human inquiry, we have developed the capacity to conceptually extend our brief moment of awareness to encompass both the deep cosmic past and the far future. We can trace our origins back to the Big Bang and project the fate of our universe trillions of years hence. This ability to transcend our immediate experience through imagination and reason represents one of consciousness's most remarkable features, and perhaps one of the universe's most extraordinary achievements. As we continue our journey through cosmic history, we next explore a possibility that further expands our conceptual horizons, that our universe might be just one among many in a vast or even infinite multiverse. This perspective challenges us to consider whether the cosmos is even larger and more diverse than we have imagined, comprising not just one universe with a single history and destiny, but a plurality of universes, each with its own physical laws, constants, and evolutionary trajectory. Our journey through cosmic history has taken us from the fiery beginning of space and time to the vast expanding cosmos we observe today. We've witnessed the birth of stars, the formation of galaxies, and the emergence of life itself. But perhaps the most profound question remains: is our universe, this entire 93 billion light-year-wide expanse of space, time, matter, and energy, just one of many? The concept of a multiverse, a theoretical framework in which multiple universes exist, alongside or beyond our own, has moved from the realm of science fiction to serious scientific inquiry. What once seemed like fantasy has become a provocative hypothesis, supported by several branches of theoretical physics. But why would physicists even consider such a seemingly outlandish idea? The answer lies in the mathematical frameworks that best explain our universe's behavior. As we've developed more sophisticated theories about fundamental physics, we've repeatedly encountered hints that our universe might be just one manifestation of a much larger reality. Let's explore the various multiverse theories that have emerged from modern physics, each suggesting different ways in which other universes might exist in relation to our own. Eternal inflation theory offers perhaps the most widely discussed multiverse scenario. According to this theory, the period of rapid cosmic inflation that occurred in the first fraction of a second after the Big Bang didn't happen uniformly. Instead, inflation stopped in some regions, like our observable universe, while continuing elsewhere. This creates a vast, eternally inflating space in which bubble universes like ours continually form and expand. Imagine a cosmic foam of bubbles, each bubble a separate universe with potentially different physical laws, different constants, and different histories. Our universe would be just one bubble in this ever-expanding foam. The space between these bubbles would continue inflating forever, pushing the bubbles further apart at speeds faster than light, making it impossible for information to travel between them. This model stems directly from our understanding of inflation, which we discussed earlier, as the rapid expansion of the early universe. Theoretical physicist Alan Guth originally proposed inflation to explain why our universe appears so uniform in all directions, and why it's geometrically flat. But the mathematics suggested that once inflation begins, it becomes difficult to stop it completely. Instead, inflation ends only in particular regions, creating pocket universes like our own. The eternal inflation model predicts an infinite number of universes, each potentially varying in fundamental ways. Some might collapse almost immediately, while others might expand for trillions of years. Some might be incapable of forming atoms, while others might develop physics even more conducive to complexity than our own universe. A different approach to the multiverse comes from string theory, our most ambitious attempt to unify the forces of nature. String theory proposes that all particles and forces arise from tiny vibrating strings in higher dimensional space. But when physicists worked out the mathematics, they discovered something unexpected. String theory doesn't provide just one solution, but potentially 10 to the power of 500 different possible universes, each with different physical laws. This vast landscape of possible universes raised a perplexing question. Why does our universe have the specific physical constants and laws that it does? Out of this enormous number of possibilities, how did we end up in a universe with precisely the right conditions for stars, galaxies, and life? Some physicists propose a mathematical multiverse based on the many worlds interpretation of quantum mechanics. According to this interpretation, every time a quantum event could resolve in multiple ways, reality splits, creating separate universes for each possible outcome. This would mean that every quantum choice, every time an electron could go left or right, or a photon could be polarized in different directions, generates a new universe. If true, this would create an unimaginably vast number of parallel universes, differing from our own in ways both subtle and profound. In some, you might have made different life choices. In others, the course of human history might be entirely different. And in many others, the fundamental constants might vary so dramatically that stars and planets never formed. These quantum multiverses would exist in the same space as our universe, but in different branches of a universal wave function, forever inaccessible to us, yet mathematically necessary for quantum theory to make sense without the need for wave function collapse. Some theories propose that our entire universe might have emerged as a particularly large and persistent quantum fluctuation. In this scenario, before the Big Bang, there existed a quantum vacuum state, a potentiality from which universes could emerge spontaneously through quantum processes. Our cosmos would be one actualized possibility from an infinite sea of potential realities inherent in this quantum substrate. This quantum cosmology suggests that nothingness itself may be unstable. Given the laws of quantum mechanics, perfect non-existence cannot persist. Something will eventually emerge from nothing through quantum fluctuations. The philosopher's ancient question, why is there something rather than nothing, might have a surprising answer, because nothing is fundamentally unsustainable according to the deepest laws of nature. The concept of a multiverse also emerges from inflation theory, the idea that the universe underwent an incredibly rapid expansion in its first fraction of a second. This inflationary period explains many observed features of our cosmos, from its remarkable uniformity across vast distances to the specific pattern of temperature variations in the cosmic microwave background radiation. According to eternal inflation, this process never completely stops. While inflation ended in our observable region, allowing galaxies and stars to form, it continues in distant regions beyond what we can see. This ongoing inflation creates an infinitely branching structure of bubble universes, each with potentially different physical constants and laws. In this scenario, before our Big Bang, the fabric of reality was already generating universes in an eternal process without beginning. Some scientists have explored whether the laws of thermodynamics might offer clues about pre-Big Bang conditions. Our universe displays a remarkable arrow of time. We clearly distinguish past from future through entropy's inexorable increase. Systems naturally evolve from ordered to disordered states. Yet the early universe appears to have been in an extraordinarily low entropy, highly ordered state. Why would a universe born from chaos begin in such a precisely ordered configuration? The physicist Roger Penrose proposed a conformal cyclic cosmology that addresses this puzzle. In this model, the far future of one universe, when all matter has decayed and black holes have evaporated, leaving only massless particles in an effectively infinite space, becomes mathematically equivalent to the conditions of a new Big Bang. The end of one cosmic eon seamlessly transitions into the beginning of another, potentially continuing forever in both directions. This theory suggests that before our Big Bang was the remote future of a previous universe, one that had expanded to such an extent and existed for so long that all complex structures had dissolved into radiation. Time and scale lose meaning at this transition point, allowing the final state of one universe to serve as the initial conditions for the next. Some attempts to unify quantum mechanics and general relativity, our most successful theories of the very small and the very large, have led to frameworks where time itself may not be fundamental. In certain approaches to quantum gravity, time emerges from more basic quantum relationships rather than existing as an independent dimension. If these models prove correct, the very concept of before might be a macroscopic approximation rather than a fundamental aspect of deep reality. In such timeless physics, asking about before the Big Bang might be like asking about the temperature of a single atom, a question that applies a concept relevant at one scale to a context where it loses coherent meaning. The Big Bang wouldn't be the beginning of time, but rather the boundary of where time itself becomes a useful concept for describing reality. The anthropic principle offers yet another perspective on pre-Big Bang conditions. This principle notes that any universe we observe must have precisely the properties that allow observers to exist. Among potentially infinite universes with different physical constants and initial conditions, we necessarily find ourselves in one compatible with our emergence. This observation selection effect might explain why our universe appears so exquisitely tuned for complexity and life. If multiple universes exist, or have existed, with varying properties, observers would only arise in the subset where conditions permit their evolution. Our universe's seemingly perfect calibration for life might not be an astonishing coincidence or the result of design, but rather an inevitable consequence of cosmic natural selection. Perhaps the most speculative multiverse theory comes from the idea of the brane multiverse in M-theory, an extension of string theory. In this picture, our universe exists on a multidimensional membrane or brane, floating in a higher dimensional space sometimes called the bulk. Other branes may exist in this same higher dimensional space, potentially interacting with our own. This brane multiverse differs from others in a crucial way. These other universes might occasionally interact with ours through gravitational effects. Some physicists have even suggested that certain anomalies in the cosmic microwave background radiation might be bruises where our universe has collided with another brane. Even beyond these frameworks, other multiverse theories include the mathematical multiverse, proposed by physicist Max Tegmark, who suggests that any mathematically consistent universe must physically exist somewhere. By this reasoning, any universe that can be described by mathematics, even those with radically different physical laws, must be real in some sense. But the key question remains: is the multiverse a testable scientific theory, or is it more philosophy than physics? Critics argue that since we cannot observe other universes by definition, the multiverse concept strays beyond the boundaries of empirical science. Defenders respond that indirect evidence might support multiverse theories. For example, if our universe shows signs of having collided with another one, or if certain features of our universe make more sense as part of a multiverse than as a unique creation, the apparent fine-tuning of physical constants, values that seem suspiciously perfect for life to emerge, might be better explained by a multiverse than by either incredible cosmic luck or intelligent design. However, we should approach these ideas with scientific caution. Extraordinary claims require extraordinary evidence, and while the mathematics of modern physics might hint at multiple universes, we must remember the difference between what's mathematically consistent and what's empirically proven. If other universes do exist, what might they look like? The answer depends entirely on which multiverse theory is correct. In the eternal inflation scenario, other universes might have completely different physical laws. They might have different values for fundamental constants, like the strength of gravity or the mass of the electron. Some might be dominated by antimatter rather than matter. Others might have 5 fundamental forces instead of our 4, or different numbers of spatial dimensions. In some universes, stars might never form because gravity is too weak. In others, atoms might never stabilize because the electromagnetic force is too strong. Many universes might be completely inhospitable to life as we understand it. But given an infinite number of universes, an infinite number would also contain the right conditions for life, perhaps even life forms far more diverse and complex than anything on Earth. In the many worlds interpretation of quantum mechanics, most parallel universes would be nearly identical to our own, differing only in the outcomes of quantum events. The farther back in time these differences occurred, the more dramatically different these universes might be from our own. Some might be so similar that the only difference is the position of a single electron, while others might have evolved completely different galactic structures or even different laws of physics if quantum fluctuations in the early universe resolved differently. Can we ever detect or communicate with these other universes? The disappointing answer, according to most physicists, is no. In eternal inflation, other bubble universes are receding from us faster than light due to the expanding space between us. In the many worlds interpretation, parallel universes exist in separate branches of the wave function, with no information transfer possible between them, according to current understanding. However, science often advances by discovering what once seemed impossible. Perhaps future theoretical breakthroughs will suggest ways to test multiverse theories more directly. Some physicists have proposed that tiny gravitational effects from neighboring branes might be detectable with advanced instruments. Others suggest that quantum entanglement might somehow connect parallel quantum universes, though this remains highly speculative. The multiverse concept raises profound philosophical questions that extend beyond physics. If infinite universes exist with every possible variation of physical laws and histories, what does that mean for concepts like uniqueness, purpose, or even free will? In a multiverse where every possible choice is realized in some universe, what meaning can we attribute to our decisions? Some argue that the multiverse provides a natural explanation for the apparent fine-tuning of our universe for life. Rather than requiring a designer who carefully calibrated physical constants to allow for stars, planets, and biology, the multiverse suggests that all possible combinations exist somewhere, and we naturally find ourselves in one of the universes capable of supporting our existence. This application of the anthropic principle remains controversial, but offers a potential naturalistic explanation for cosmic fine-tuning. Others see the multiverse as diminishing the specialness of our universe. If ours is just one of countless universes, perhaps there's nothing particularly significant about our cosmic home. Yet one could also argue the opposite, that in a vast multiverse of mostly hostile universes, the precious rarity of life-supporting worlds like ours makes them more extraordinary, not less. The multiverse concept has roots that stretch back surprisingly far in human thought. Ancient Hindu cosmology described multiple worlds being created and destroyed in endless cycles. Some Buddhist traditions envisioned countless world systems existing simultaneously. The concept appears in various forms across human cultures, perhaps reflecting a persistent intuition that reality might be larger than what we can observe. In modern times, the multiverse has permeated popular culture through science fiction, film, and literature. Stories of parallel worlds where history took different turns, or where physical laws operate differently, have captured our imagination for decades. While these fictional multiverses often differ significantly from the scientific theories, they speak to the same human fascination with possibilities beyond our observable reality. For scientists, the multiverse represents both opportunity and challenge. It offers potential solutions to long-standing puzzles in physics, such as why our universe has precisely the properties it does. Yet it also pushes at the boundaries of what we can test and observe, requiring new approaches to scientific methodology. Some physicists, including luminaries like Roger Penrose, remain skeptical of multiverse theories, arguing that they're too speculative and potentially unfalsifiable. Others, like Andre Linde and Brian Greene, see the multiverse as a natural extension of our most successful physical theories, worthy of serious consideration despite the observational challenges. The debate continues in scientific journals and conferences worldwide, with proponents and skeptics alike contributing to our understanding of these possibilities. What's remarkable is that this discussion is happening at all, that human knowledge has advanced to the point where we can reasonably contemplate realities beyond our observable universe based on mathematical models and theoretical physics. As we look to the future of multiverse research, several avenues appear promising. Advanced space-based telescopes might detect subtle patterns in the cosmic microwave background radiation that could support or contradict specific multiverse models. New experiments at particle accelerators could reveal extra dimensions predicted by string theory. Theoretical advances might suggest new, unexpected ways to test these ideas. The concept of the multiverse reminds us of the extraordinary journey of human understanding. We began as a species gazing at the night sky, imagining ourselves at the center of a single world. We gradually discovered that Earth is one planet among many, orbiting an ordinary star in one galaxy among billions. Now we contemplate the possibility that our entire universe, this vast, ancient expanse of space and time, might be one among countless others in a reality far larger and more diverse than we ever imagined. Whether the multiverse ultimately proves to be a profound insight into the nature of reality or a fascinating but unprovable speculation, the quest to understand it embodies the human spirit of exploration. Just as our ancestors ventured beyond the horizon to discover new lands, today's theoretical physicists push beyond the observable universe, using mathematics and reason as their ships of discovery. As we prepare to conclude our cosmic journey, we're left with a humbling perspective. If the multiverse exists, our universe, despite its billions of galaxies and trillions of stars, is just one chapter in an infinite cosmic library. Yet far from diminishing the importance of our story, this perspective invites us to appreciate the extraordinary rarity and preciousness of our cosmic home, and to continue exploring its mysteries with wonder and determination. Our journey through space and time now brings us to our final chapter, where we'll reflect on what the history of the universe means for humanity and what the future might hold for the cosmos we call home. As our cosmic journey draws to a close, we find ourselves at a unique vantage point, looking back across 14 billion years of cosmic evolution, while simultaneously peering into the possible futures that await. From the incomprehensible conditions of the Big Bang to the vast, expanding cosmos we inhabit today, we have traversed the greatest story ever told, the history of everything that exists. What have we learned from this grand cosmic narrative? Perhaps most profoundly, we've discovered our place in the universe, not at its center as our ancestors once believed, but as participants in an ongoing cosmic drama that began long before us and will continue long after we're gone. We are, in a very real sense, the universe becoming conscious of itself. Collections of atoms that have organized themselves into beings capable of contemplating their own origins. Our journey began with the ultimate question: how did everything come to be? We explored the moment of creation itself, the Big Bang, when space, time, energy, and the laws of physics burst into existence. We witnessed the universe's first moments, when it expanded from a size smaller than a subatomic particle to a vast expanse in less than a second. We saw how the fundamental forces separated, how quarks and gluons formed the first protons and neutrons, and how the lightest elements, hydrogen and helium, emerged from the cooling cosmic furnace. For 380,000 years, the universe remained an opaque fog of charged particles until it cooled enough for the first atoms to form, releasing the oldest light in the universe, the cosmic microwave background radiation that still surrounds us today, a fossil record of the infant cosmos. This ancient light has confirmed many of our theories about cosmic origins and remains our most distant window into the past. Then came the cosmic dark ages, a period lasting hundreds of millions of years when no stars illuminated the expanding void. During this time, subtle fluctuations in the distribution of matter, influenced by the gravitational pull of dark matter, began to grow and coalesce. These cosmic seeds would eventually become the first stars and galaxies. Around 400 million years after the Big Bang, the darkness was pierced by the first starlight, as massive, short-lived stars ignited, living brief but brilliant lives before exploding as supernovae. These cosmic furnaces forged heavier elements like carbon, oxygen, and iron, the building blocks that would eventually form planets and, on at least one world, life itself. The universe had begun the process of creating chemical complexity. The first galaxies formed as gravity pulled these early stars together, creating the large-scale structure we observe today, a cosmic web of galaxy clusters and superclusters separated by vast voids. Our own Milky Way galaxy took shape during this period, ultimately growing into a spiral galaxy containing hundreds of billions of stars. Within one ordinary spiral arm of this ordinary galaxy, a cloud of gas and dust began to collapse about 4.5 billion years ago. At its center formed our Sun, while in the surrounding protoplanetary disk, the planets of our solar system took shape through countless collisions of rock, ice, and dust. Earth formed as a molten world that gradually cooled, developing an atmosphere and oceans as impacts from water-bearing comets and asteroids delivered the ingredients for what would become a living planet. And then, through processes we're still working to fully understand, life emerged. First as simple single-celled organisms, then gradually evolving into the complex biosphere we know today. Through billions of years of evolution, punctuated by mass extinctions and recoveries, life diversified into millions of species, eventually producing beings capable of looking back and reconstructing this entire cosmic history. This unbroken chain of events, from the Big Bang to human consciousness, represents an extraordinary journey of increasing complexity and organization. Against the backdrop of an expanding universe and the increase of entropy, life stands as a remarkable countercurrent, a local decrease in disorder that emerges from the universe's physical laws. Yet our exploration hasn't been limited to the past. We've also peered into the cosmic future, extrapolating from current observations to consider the universe's ultimate fate. We've learned that the expansion of the universe is accelerating, driven by the mysterious force we call dark energy. If this acceleration continues, the universe faces a big freeze, a future where galaxies recede beyond our cosmic horizon, stars burn out, black holes evaporate, and even atoms may eventually decay, leaving a cold, dark, featureless void in the unimaginably distant future. Perhaps most provocatively, we've contemplated the possibility that our universe is just one of many, a single bubble in an infinite cosmic foam, or one branch of an endlessly dividing quantum tree. The multiverse hypothesis, suggests our cosmic story might be just one volume in an infinite library of possible universes, each with its own physical laws and histories. Throughout this journey, we've repeatedly encountered the limits of our knowledge. For all that modern science has revealed about cosmic history, profound mysteries remain. What caused the Big Bang? What is dark matter made of? Why does dark energy exist? Are there other universes? These questions may be answerable with future discoveries, or they may represent the boundaries of what human science can know. The history of cosmology itself provides valuable perspective. For thousands of years, humans created myths and religious narratives to explain cosmic origins. In just the last century, we've developed a scientific account based on observable evidence and mathematical models that has radically transformed our understanding. From Edwin Hubble's discovery of cosmic expansion to the detection of gravitational waves, each breakthrough has refined our cosmic story. This scientific narrative continues to evolve as new observations challenge old theories and new technologies extend our visual reach deeper into space and time. One of the most profound aspects of our cosmic history is the role of time. The universe has existed for around 14 billion years, a span so vast that human history occupies just the thinnest slice of cosmic time. If the entire history of the universe were compressed into a single Earth year, human civilization would emerge only in the final minutes of December 31st. Yet in that cosmically brief moment, we've managed to reconstruct nearly the entire 14 billion year history that preceded us. The universe has no obligation to be comprehensible to the human mind, yet remarkably, we've been able to decipher much of its story. The mathematical patterns discovered by scientists from Newton to Einstein to current theoretical physicists have proven astonishingly effective at explaining cosmic processes. This unreasonable effectiveness of mathematics, as physicist Eugene Wigner called it, suggests a deep order to reality that our minds can grasp, despite evolving on a single planet around an ordinary star. Our cosmic understanding raises profound philosophical questions that transcend science itself. Why does the universe exist at all, rather than nothing? Why does it have the particular properties that allow for complexity and life? Is the apparent fine-tuning of physical constants evidence of a multiverse, of purpose, or simply a cosmic accident? These questions blend physics with philosophy, science with existential inquiry. Perhaps one of the most striking discoveries is cosmic abundance. The observable universe contains roughly 2 trillion galaxies, each with hundreds of billions of stars. Recent discoveries of exoplanets suggest that most stars host planetary systems, with billions of potentially habitable worlds in our galaxy alone. The ingredients for life, carbon, hydrogen, oxygen, nitrogen, are cosmic commonplaces, forged in the hearts of stars and scattered by supernovae. This cosmic perspective simultaneously highlights both our insignificance in the grand scheme and the extraordinary conditions that allowed for our existence. The very atoms in our bodies have cosmic histories. The carbon in our cells, the oxygen we breathe, the iron in our blood, all were created inside ancient stars that exploded billions of years ago, scattering these elements across space, where they eventually became incorporated into our solar system and, ultimately, into us. As astronomer Carl Sagan famously noted, we are quite literally star stuff, the universe made conscious and contemplating itself. This profound connection to cosmic history offers a perspective that transcends cultural, national, and even religious boundaries. When we look at Earth from space, we see no borders, only a fragile blue marble suspended in the black void, the only home we've ever known, a tiny oasis of life in an unimaginably vast cosmos. This overview effect, described by many astronauts, emphasizes our shared destiny and responsibility for our planetary home. The technological fruits of cosmic understanding have transformed human life. From the GPS satellites that guide our journeys to the telecommunication networks that connect us globally, from the medical imaging technologies developed from astronomical instruments to the solar panels converting starlight to electricity, cosmic science has yielded practical benefits beyond measure. our quest to understand the stars has repeatedly improved life on Earth. Looking forward, cosmic awareness also highlights existential challenges. We now understand that Earth has experienced numerous mass extinctions triggered by cosmic events, like asteroid impacts. We recognize that the Sun will eventually expand and make Earth uninhabitable. In the much nearer term, we face human-caused climate change that threatens our civilization. Cosmic perspective doesn't diminish these challenges, but places them in context and potentially provides solutions. The history of the universe also offers perspective on human conflicts and concerns. Against the backdrop of cosmic time, many of our divisions seem petty and short-sighted. The universe has existed for 14 billion years and may continue for trillions more. Our species has existed for merely 200,000 years, and our recorded history spans only a few thousand. This cosmic timescale invites us to consider our legacy. What kind of future do we want for humanity among the stars? Perhaps the most profound lesson from cosmic history is the preciousness of consciousness itself. As far as we know, Earth is the only place where the universe has become aware of itself, where matter has organized into beings capable of contemplating their own origins and future. Whether or not other intelligent life exists elsewhere, the emergence of consciousness represents a remarkable development in cosmic evolution, the universe generating observers of itself. The scientific story of the universe doesn't replace the human need for meaning, but offers a foundation upon which meaning can be built. Far from diminishing our significance, cosmic awareness can enhance it by revealing our deep connection to the entire cosmic story. We are not separate from the universe, but an integral part of its ongoing evolution. Our cosmic journey continues beyond this documentary. Every day, telescopes capture new images of distant galaxies, spacecraft explore our solar system, and theorists propose new ideas about cosmic origins and destinies. The James Webb Space Telescope peers deeper into space and time than ever before, perhaps soon detecting biosignatures on exoplanets or revealing the light of the first stars. Gravitational wave observatories open new windows into cosmic events, letting us hear the universe in ways impossible just a decade ago. As we conclude our journey through cosmic history, we're left with a paradox. We know more about the universe than any generation before us, yet we've also discovered how much remains unknown. For every question answered, new mysteries emerge. This is not a failure, but the nature of exploration itself. The horizon of knowledge continuously expands, revealing new territories to discover. The story of the universe is not finished. It continues to unfold, with humanity playing a unique role as both observers and participants. Whether our species survives for thousands, millions, or billions of years, whether we remain confined to Earth or spread throughout the stars, we are part of the cosmic story. Our decisions and actions today will shape the next chapter of this greatest of all stories. In the grand cosmic perspective, our lives are fleeting. Yet in our brief moment, we've accomplished something extraordinary. We've reconstructed the 14 billion year history that led to our existence. We've traced our origins back to the stars, to the earliest atoms, to the Big Bang itself. We've discovered that we are connected to everything that exists, participants in the ongoing evolution of a universe that produced beings capable of contemplating their own origins. The universe began in fire and may end in ice. But between those cosmic bookends exists the remarkable story of matter organizing itself into ever more complex forms, eventually producing beings capable of love, art, science, and wonder. Whether the universe exists for a purpose or by chance, our ability to contemplate these questions and seek meaning is itself a profound feature of cosmic history. Our journey through the history of the universe doesn't end with this conclusion. It continues in every scientific discovery, in every child looking up at the stars in wonder, in every human being contemplating their place in the cosmos. The greatest story ever told remains unfinished, with new chapters being written by each generation. What role will we play in this cosmic drama? What discoveries await future explorers of space and time? These questions await answers as the never-ending story of the universe continues to unfold. As we gaze up at the night sky, we're looking at our cosmic home, our origin story written in starlight. The history of the universe is our history. The future of the universe is, at least in some small measure, ours to influence. In that profound connection between the cosmic and the human lies perhaps the greatest insight of all. We are not merely observers of the universe, but an integral part of its ongoing evolution, consciousness emerging from stardust, the cosmos contemplating itself. Some theorists have even explored whether intelligence from previous cosmic cycles might influence subsequent universes. In a far future civilization confronting the end of its universe, might advanced beings find ways to seed initial conditions for the next cosmic cycle, ensuring the emergence of complexity? While highly speculative, such scenarios highlight how pre-Big Bang questions inevitably entangle scientific and philosophical considerations about purpose, continuity, and information preservation across cosmic transitions. Mathematical physicists have identified another intriguing possibility. Our universe might be a simulation running within a more fundamental reality. While this scenario sounds like science fiction, it arises naturally from considering the computational nature of physical laws and the theoretically achievable computing capacity of advanced civilizations. If consciousness can be simulated and vast computing resources exist in a base reality, the number of simulated universes could vastly outnumber the original. In this simulation hypothesis, before our Big Bang would be the computational substrate of the parent universe, a reality perhaps utterly unlike our own, operating according to different physical principles that allow for the simulation of entire cosmos like ours. While currently untestable, this perspective reminds us that apparent beginnings might be transitions between levels of reality rather than absolute origins. As we contemplate these diverse theories about pre-Big Bang conditions, we confront a profound limitation. Our current laws of physics break down as we approach the Big Bang itself. The extreme densities and energies of the earliest moments exceed our ability to describe them with established theories. General relativity predicts a singularity, a point of infinite density where space-time itself becomes ill-defined. Quantum mechanics suggests fluctuations would dominate at these scales, but we lack a complete quantum theory of gravity to describe this regime precisely. This theoretical boundary is known as the Planck epoch, the first 10 to the negative 43 seconds after the apparent beginning, when the universe was smaller than a subatomic particle. Beyond this frontier, our mathematical descriptions become inadequate. The question of what came before necessarily involves speculation about realms beyond our current theoretical reach. String theory, loop quantum gravity, causal set theory, and other approaches attempt to peer beyond this Planck barrier, but all remain works in progress. Each offers mathematical frameworks that might eventually describe the transition from pre-Big Bang conditions to our observable cosmos, but none has achieved the status of a complete, experimentally verified theory. Despite these limitations, cosmologists continue searching for observable consequences of various pre-Big Bang scenarios. Certain models predict specific patterns in the cosmic microwave background radiation, the oldest light in the universe. Others suggest particular distributions of galaxies on the largest scales, or distinctive gravitational wave signatures that might be detected by future instruments. While we cannot directly observe pre-Big Bang conditions, their echoes might be discernible in the structure of our observable universe. The concept of cosmic inflation, that explosive expansion in the universe's first fraction of a second, offers potential clues. The specific pattern of density fluctuations preserved from this inflationary period might reveal whether our universe emerged from a quantum fluctuation, a previous cosmic cycle, or some other pre-existing state. Advanced space telescopes and gravitational wave detectors might eventually find evidence favoring one pre-Big Bang scenario over others. As we stand at the current frontier of cosmological understanding, we might be witnessing a transition comparable to ancient seafarers who once believed the ocean simply ended at the horizon. Just as exploration revealed greater oceans beyond those visible boundaries, future theoretical and observational advances may extend our cosmic horizon beyond the apparent beginning we call the Big Bang. This quest to understand what, if anything, existed before the beginning represents science at its most profound, pushing against the boundaries of the knowable, seeking mathematical frameworks that might extend our understanding beyond apparent limits, and pursuing observational evidence that could distinguish between competing visions of ultimate origins. Whatever existed before the Big Bang, whether a quantum vacuum, a previous cosmic cycle, a higher dimensional brain, an inflating metaverse, or something we've not yet imagined, the quest to understand it stands as one of humanity's most ambitious intellectual endeavors. It reminds us that the horizon of knowledge is not fixed but expanding, much like the universe itself. Now, let's dive into the moment when everything as we know it began, the Big Bang itself, where our theoretical understanding becomes more grounded in observational evidence, and the history of our universe truly begins to unfold. 13.8 billion years ago, our universe erupted into existence. In a flash more brilliant than a trillion suns, space, time, matter, and energy burst forth from a point infinitely dense and infinitesimally small. This moment, the Big Bang, marks not just the birth of our cosmos, but the beginning of physical reality as we understand it. It was not an explosion in pre-existing space, but the explosive beginning of space itself. A moment when the very fabric of reality began to expand, stretch, and cool from conditions so extreme they defy imagination. The term Big Bang might conjure images of a conventional explosion, with debris flying outward from a central point into surrounding emptiness. But this picture fundamentally misrepresents what occurred. There was no outside into which the universe exploded, no pre-existing void to receive the newborn cosmos. Instead, space itself came into being and immediately began expanding everywhere, carrying the primordial energy of creation with it. Every point in the universe experienced this expansion simultaneously, like the surface of a balloon inflating in all directions at once. In its earliest moments, our universe was unimaginably hot, with temperatures reaching into the trillions and trillions of degrees. At such extreme temperatures, matter as we know it could not exist. Even atoms, much less molecules or larger structures, would have been instantly torn apart. The entire universe was a seething plasma of elementary particles and pure energy, so dense that light itself could not travel freely. The familiar laws of physics as we understand them today were compressed into a unified force, indistinguishable from one another in this furnace of creation. The initial expansion happened at an incomprehensible rate, in the first fraction of a second, an interval so brief it defies everyday comparison. The universe underwent a period of exponential growth called cosmic inflation. During this inflationary epoch, lasting from approximately 10 to the negative 36 seconds to 10 to the negative 32 seconds after the Big Bang, the universe expanded faster than the speed of light. While nothing can travel through space faster than light, space itself has no such speed limit. It can expand at any rate. This extraordinarily rapid expansion increased the size of the observable universe by a factor of at least 10 to the 26 in just a tiny fraction of a second. To grasp this scale, imagine a pebble expanding to become larger than the entire visible universe we observe today, and all of this happening in an interval shorter than it takes light to cross the diameter of a proton. Inflation represents the most extreme growth spurt in cosmic history, a moment when the universe stretched so violently and rapidly that its size increased by a factor greater than a trillion in less time than it takes to blink. Why did this inflation occur? According to the leading theoretical models, in the first instance after the beginning, the universe was dominated by an energy field sometimes called the inflaton field. This field existed in a highly unstable state, like a ball perched precariously at the top of a hill. As this field began to settle into a more stable configuration, like that ball rolling down to the valley below, it released enormous energy, driving space to expand at this exponential rate. When inflation ended, this energy converted into a hot, dense soup of particles and radiation, setting the stage for the more gradual expansion we observe today. Inflation solved several profound puzzles about our universe. It explains why the cosmos appears so remarkably uniform across vast distances, regions so far apart they could never have communicated with each other through conventional means. Before inflation was proposed, this uniformity seemed to violate causality, since opposite sides of the observable universe would have been too distant from each other to have ever been in contact. Inflation resolves this horizon problem by revealing that these now distant regions were actually in close proximity before inflation stretched them apart. Inflation also explains why the geometry of space appears so precisely flat. Just as stretching a wrinkled piece of fabric makes it appear smooth, inflation would have stretched any initial curvature of space until it became effectively undetectable, just as we observe today. Without inflation, this precision would seem like an extraordinary coincidence, requiring the initial density of the universe to have been fine-tuned to an implausible degree of accuracy. Perhaps most significantly, inflation explains the origin of the large-scale structure we observe in today's universe. Quantum fluctuations, tiny random variations in energy density that arise from the uncertainty principle of quantum mechanics, would have been present during the inflationary epoch. Inflation stretched these microscopic quantum jitters to macroscopic scales, creating subtle variations in density across the expanding cosmos. These variations served as the seeds for all future structure, the places where matter would eventually collect to form galaxies, stars, planets, and eventually us. As inflation ended, the enormous energy that had driven the exponential expansion converted into particles through a process physicists call reheating. The universe became filled with a super-hot plasma of elementary particles and their antiparticles, colliding and annihilating in a frenzy of creation and destruction. This marks the beginning of the more familiar hot Big Bang phase of cosmic evolution, the starting point for the gradual expansion and cooling that would eventually lead to the universe we observe today. In the first microseconds after inflation, when temperatures still reached trillions of degrees, the universe consisted of a soup of fundamental particles unlike anything we can recreate even in our most powerful particle accelerators. During this quark epoch, the basic building blocks of protons and neutrons, quarks and gluons, floated freely in a state of matter called a quark-gluon plasma. So extreme were the conditions that quarks could not bind together into composite particles as they do in today's universe. As the universe continued expanding and cooling, reaching temperatures of about 10 trillion degrees, still hotter than the center of the most massive stars, another profound transition occurred. Quarks began binding together to form protons and neutrons in a process called baryogenesis. This transition, occurring when the universe was about 1 microsecond old, marked the formation of the first stable matter particles that would eventually form the nuclei of atoms. During this same early period, something deeply mysterious happened. An asymmetry developed between matter and antimatter. According to our understanding of particle physics, the Big Bang should have created equal amounts of matter and antimatter, which would then have annihilated each other completely, leaving only radiation. The fact that our universe contains abundant matter but virtually no naturally occurring antimatter reveals that some process in these early moments created a slight imbalance, perhaps just 1 extra matter particle for every 10 billion antimatter particles. This tiny asymmetry, the origin of which remains one of the great unsolved problems in physics, is ultimately responsible for the existence of all the matter in our universe today. By the time the universe was 1 second old, another crucial transition had occurred. The universe had cooled enough for the first of the 4 fundamental forces of nature to separate from the others. In the extreme conditions of the earliest universe, the electromagnetic force, the weak nuclear force, the strong nuclear force, and gravity were unified into a single interaction. As temperatures dropped, these forces separated in a process physicists call symmetry breaking. At 1 second after the Big Bang, 3 of these forces, electromagnetic, weak, and strong, had assumed their distinct identities, though the electromagnetic and weak forces would remain unified for a bit longer as the electroweak force. This era also saw the production of the lightest elements through a process called Big Bang nucleosynthesis. When the universe was between 1 and 3 minutes old, temperatures had fallen to about 1 billion degrees, comparable to the interior of massive stars today. Under these conditions, protons and neutrons could fuse to form the nuclei of deuterium, heavy hydrogen, helium, and trace amounts of lithium. Remarkably, about 25% of all the ordinary matter in the universe was converted to helium during these few crucial minutes. The precise abundances of these light elements that we observe today serve as one of the strongest pieces of evidence for the Big Bang theory. For the next few 100,000 years, the universe continued its expansion and cooling, but remained opaque to light. The cosmic plasma was still hot enough that any atoms that formed would be immediately torn apart by the intense high-energy radiation. Free electrons scattered photons in all directions, preventing light from traveling in straight lines. The universe was like a dense fog, with radiation and matter locked in a dynamic equilibrium, a state physicists call tightly coupled.